Welcome to all of you. My name is Krishna Nandivada, and I have with me my co-author Aman Naugra here, or rather the main author of IMOP. And this is the tutorial about IMOP. IMOP is the IIT Madras OpenMP compiler framework. Okay. All right. If you look at the internet, it's kind of, there are tons of compiler frameworks. I mean, I'm pretty sure we think that we have listed pretty much all of the compiler frameworks, but there will be many that we have not listed, right? I mean, these are, and also this is just a subset of the static compilers. There are also more dynamic compilers. I mean, each compiler comes with their own compilation goals. So with so many compilers already around, right? The question, I mean, one would ask is, this should be enough. Why do we need one more, right? And again, with that statement that why do we need one more, we have one more. And we call it the IMOP. This is a tutorial on that. But why, right? I mean, why do we want one more this thing? So it so turns out, typically a compiler is built with a specific goal in mind. I mean, if you look at GCC or LLVM, right, two of the most popular compiler frameworks, they work at a low-level program representation. Most of the analysis and optimizations they do are at low level, and then comes this notion of, so what if it is low level, right? See, our target, as we said before, is OpenMP programs, right? This is a compiler framework for OpenMP programs. As you know, the OpenMP, all the directives, which are directives on top of C or C++ programs, they are typically high-level annotations, right? So the programmer expresses them at a high level, and if you look at any OpenMP related optimization or analysis, any of these papers, you will see that they are all expressing the program analysis logic at a high level. All right, high level as in transform these constructs in this way. If the constructs are in this way, do this, right? So the analysis logic, the optimization logic is typically understood and expressed using higher level constructs, okay? Then if you want to analyze these applications using things like GCC or LLVM, these abstractions are not directly supported. So you will be dealing with lower level syntaxes. They're all function calls at some level. So these compilers, most of these are built for serial programs. As a result, the implementations of analysis and transformations, first of all, they're difficult if you want to directly port them to OpenMP. If you don't care about it and directly use those for OpenMP programs, then it could be even incorrect. Why? Because parallel programs have their own semantics, which cannot directly use serial program related analysis or optimizations, right? For instance, the static analysis do not assume multiple threads of execution. They do not know anything about the memory consistency models. The inter-thread or inter-task data flow is not modeled. And that boils down all the way down to the compiler. The compiler also doesn't know anything about these data flow across threads. You have to manually handle them. Okay. And let me ask this, let me take this time to ask a question. Have any one of you written any compiler analysis or optimization as part of your class homework or anywhere else or your project work? Anyone? Please unmute and answer. If you are having difficulty in talking, then put it in the chat window. Any pass in a compiler or any analysis that you might have written. Let me, maybe people are shy to start. Let me randomly pick one. Say, Jaman Park. Have you written any pass? Arvind? Rohu? By the way, am I audible?
Yes, you are.
Yes. Great. All right. So if you have written any pass, see, let's say you want to do some compiler optimization that will remove some dead code, right? Or any such optimization. Then the program has changed. As a result, the compiler's internal data structures all have to change. Otherwise, we won't consider it as stable or consistent. And this has to be manually done. Okay. So if you do any optimization, we want to make sure that the information remains stable and the traditional compilers do not have any mechanism to automatically stabilize them. Right? So these are some of the reasons why we feel that no, we needed something more. Okay. For this, we have developed what we call as IMOP. It's an open source compiler framework. Uh, it targets OpenMP C code, pretty much all of the C syntax, all of OpenMP syntax it supports. It's a source-to-source translator. So it takes OpenMP C code, outputs OpenMP C code. You can bring in your own optimizations. It will do all those optimizations and output OpenMP C code. What's the advantage of that if I do source-to-source? Anyone? Let me again ask someone random. Ahmed Sharif, what's the advantage if I do source-to-source translation? Code will not get optimized. No, if I optimize and even then I emit OpenMP C code, right? So our goal is that we will be able to write many optimizations and emit in comes OpenMP C code, optimize using IMOP, out goes OpenMP C code. What's the advantage of using source-to-source as our target from OpenMP C to OpenMP C? Anyone else? Say Minesh.
Maybe that it stays human readable or interactable, I guess. Perhaps that you can interact with the optimized version as a human. You can modify the code.
Excellent point. So I can look at the optimized code and see if I can further manually optimize, or I can use existing compilers like GCC, LLVM, etc., which already have a lot of low-level optimizations ready. I can use them as it is, right? And IMOP also helps automating a lot of compiler-related processes. We already talked about stabilization. It also helps to automatically interact with Z3, constraint solver, and so on. Okay, so that's our key guiding principle. It eases the task of implementing various analysis and any transformation tools that you may want to write. Okay, it can automate many of these. Right? We have released this IMOP already, and there have been people who are using it. For instance, I'll give a brief summary. In a graduate level course here at IIT Madras, IMOP was used as an alternative to LLVM. In a class of 25, 10 used IMOP, rest used LLVM. And we just gave around 1 lecture-hour introduction to IMOP. And the students had already been using LLVM for more than 3 assignments. If you look at the average marks, the students with who used IMOP got nearly same, maybe slightly more than LLVM on average. Importantly, the code size that people had to write in IMOP was far less compared to LLVM. And their feedback was very cool. We took a survey. Compared to LLVM, people gave readability, in terms of readability of code, they gave IMOP 4.14 out of 5. Similarly, ease of coding, ease of debugging, over LLVM, the students said, oh, this is far, far better, right? I mean, they give a lot of interesting feedback orally. In terms of written feedback, there's one particular thing that it summarizes, I felt. It was far less difficult than LLVM to work with IMOP. Okay. People have already also used IMOP for quick prototyping of their compiler analysis. There have been few papers that we have listed here. If you are a person who wants to optimize or analyze OpenMP C programs, or even transform them to some other code, IMOP would be a great option. Do try it out. Okay. With that background, what we will do, we will code for the tutorial. This is our objectives. By the end of the tutorial, the participants will be able to use IMOP to prototype different program analysis techniques and optimizations. Definitely for the ones that are discussed in the tutorial, and may have an idea to proceed further. Okay? And we hope that many of you will consider IMOP for fast prototyping of your own custom analysis and optimization. Okay? At this point, I'll take a quick break and see if there are any questions. Are there any questions? No questions? All right. Fine. So, I mean, just to give you a few more insights about what you can do within this tutorial. Within 8 lines of code, you can write a loop unroller for while loops, not for loops, but while loops. You can add write barriers for a variable. You want to say, hey, whenever this variable is written to, do this, right? Some code instrumentation in just around 10 to 12 lines of code. You can even write a reasonably involved OpenMP optimization pass to remove redundant barriers in 30 lines of code, right? We feel that IMOP makes it very easy and it will be exciting, okay? If there are any questions, I'll wait for a couple of seconds, else we will begin with the tutorial. No questions? All right. We will start with our hands-on session. there is a link. I have pasted it on the chat window. Please click on the link. It will open a Google Doc and follow the instructions to start the demo. I will myself do the demo along with you guys. Yeah, I'll join you in a minute or two. So just start reading the session. I'll join you. I hope all of you have Eclipse on your systems. If you do not have Eclipse on your system or have trouble installing Eclipse and so on, please let us know. We will try to give you a virtual machine where these things are already installed. Hey, Aman, you have sent the message only to me. You want to send it to all.
Oh, sorry. Thanks.
All right. So what I will do now, I will start the sharing myself. So whoever is able to finish different steps in the Google Doc, right? Please say in the chat box that you have done step one. I mean the point G, how far you are if you make any progress or if you're stuck, please mention.
Krishna, there is some issue with the sharing right now. The screen just shows a white patch at the center.
Yeah.
It's black.
Yeah,
Okay.
let me start sharing again. All right. Has anyone succeeded in doing a Git clone? Please put it in the chat window if you don't want to if you're having issues with audio. See, we need to do this tutorial so that, I mean, the hands-on session, that will be easy for you guys to work with, right? Let me ask a question.
Hello, sir. Utpal here. So, is it possible? Is it possible to work without installing Eclipse?
Uh, yeah, you could. Just that Eclipse makes a lot of editing much faster for us. We'll save a lot of time because it will do a lot of auto filling, right?
Alternatively, we can share the VNC link to one of the pre-set up machines where we already have Eclipse in case if you want to give it a try.
Yes, please. That will be helpful.
I'll share the IP address with you. The instructions are there in that we have shared. I'll share the IP address with you.
Okay. Okay.
If any among you want to use the VPN connections, please feel free to drop me a chat message. Uh, I'll send you the IP address of the pre-set up machines. I'm sending to Utpal now. Just a minute.
All right, so now I'm starting to share my own screen with the same things that we want you to do. So let me share screen. I think I can share the whole thing. Oh, that's a better idea. I can share the full screen. All right. Share screen, desktop one. All right. So what I will do now, Aman, you can see the full screen, right?
Yes, yes, it's visible.
Okay, let me make the font slightly bigger. So I'll do a git clone. So I did the git clone. Now I'll go to Eclipse. And in Eclipse, I will go to File, New Java Project, and I'll browse to the place where I have downloaded, which is IMOP compiler, and then I'll open it. Okay, and wait. As per the instructions, I have to create I have to go to IMOP compiler and create a output dump directory that I did, and then I say finish. Then I go to IMOP compiler,
Sorry,
SRC.
the font is quite small right now.
The
It's
font
not
is
really-
too small. how do I make the font bigger?
Maybe just for the editor window once we go there. For now, I guess it's fine.
Oh, I should share only the editor, is it, you think?
Yeah, I guess that will increase the font size.
Good idea. Let me try that. Stop share. Meeting. Start sharing. And I'll share only the Eclipse window. Is it better, Aman?
Yes, it's better now, relatively.
Okay. Okay. So now I go to this SRC. Inside SRC, there is this IMOP directory. I just, this IMOP dot projects, I will say don't include in this thing. I'll extrude it from this thing. And now I'll go to demo directory. Inside demo, there is demo 0.java. I'll open it and I'll just run it. It says setup successful. Is it fine with anyone? Sorry, everyone? Or are we stuck somewhere? Is everyone fine? I see no one is saying anything. That's a bit unnerving. All right, I'm hoping that we have gotten to the end of demo 0, but if there are any questions, I'll take it. Are there any questions? Anyone in the chat? No? Okay, then we'll continue. I'm hoping that all of us have cleared the first demo. Then we'll go to the next part. Okay. Let me start sharing the screen for that. Aman, the new share is visible, right?
Yes, it is.
Okay. See, let's say we start with a simple grammar. Okay, it's a while statement. With his standard grammar, right? While keyword followed by expression followed by statement. And what can the statement be? It can be a compound statement, if statement, and so on. Now, if you want a parser to parse it, parse using this grammar, a simple while loop, it will get an AST, abstract syntax tree. This is something that we understand very well, correct? Now, what IMOP does is that it accepts programs written in standard C and nearly all of OpenMP 4.0. It can handle all standard benchmarks, NPB, SpecOMP, Sequoia, and so on. IMOP itself is written in Java, and it works at an AST level that we showed just now. Okay, and parser of IMOP has been created using Java CCJT. So if you take this input program and parse it, there is a, so in IMOP, if you invoke this command parse normalize input, and it will take a file and generate the AST. Okay, So you can pass the file name as an argument, and it will automatically create the AST and give you the control over the root. The root can be accessed using from this program class. Okay. So you can invoke it online, command line as well. For example, you can do Java IMOP.main and a file name. You remember this file name is, it is taking the pre-processed OpenMP C code. And how do you get pre-processed code? You can use GCC -C. Okay. And if you invoke this parse normalized input, it will give the parsers, the root of the parser in program.root. Okay. So now you can print your program, whatever the program you have. Very simple. What do? You take the file, okay, and invoke this parse normalize input. What does it do? It will take the file. It will generate the AST and give you the get, which you can access by calling program.getRoot. It also will simplify a bit of the code. Okay. You can also print this to the standard output by calling system.out.println. You can also write to a file by calling this function called dump_root. It will take a string as an argument f1. Remember our file name was foo.i. So this will dump to foo f1.i. Okay. Simple, right? So now we can read the input from a file, print it to standard output or a file. Okay. Let's try this. We will try this in the demo. That's coming up very soon. Just hold on. Remember, with each AST node, we maintain a subclass called node info that gives us additional information. Information about the particular AST node as well as some operations that can be performed. I can get this information by invoking getInfo. For example, look, let's say I have this statement int x equal to y plus 3. That's a node. Y plus 3 is another AST node. So I can do n1.getInfo. What is n1? It's a declaration. I can invoke a function called getInitializer that will give me a node which is n2, which is this initialization for x. Right? Simple, right? I am able to access the info object and perform some operations. Let us say my n1 is this while loop. I can also use the getInfo object to do something more. Things like I can do n1.getInfo unroll loop. So unroll loop has been already implemented in the while statement info class. So if you do unroll loop 1, it will generate the code what you see on the right side. Okay? From the input code, I can go to the output code. It will automatically generate. Nice, right? Okay? See, one normal thing that we do when we work within a compiler is that I may have to traverse the AST, right? I want to traverse over all the intermediate representation, the whole program. But traversing the AST at a low level is not very comfortable. So we don't recommend that. Better we use high-level query functions. There are many that IMOP provides. For example, give me all functions of the program. Program.getRoot. That will give me the root of the program. .getInfo. The program info object. And then I will invoke get all function definitions. Get all function definitions. Similarly, if n is a statement, I can do, sorry, if n is a statement or a statement block or a function definition, I can do n dot get info, and then I'll say give me all statements with label L by invoking the function get statement with label, and I can pass the label name. Some of you may have tried this, right? Give me all the if statements in the program. Give me all the while statements in the program. I can do something like this. Let's say in this case, I'm looking for all the if statements. I can invoke a function called misc, which stands for miscellaneous. Miscellaneous dot get inherited and close E. And I'll pass this n and say find all the nodes of type if statement dot class. It will give me all of them in a list. Very convenient. I mean, if you are a person who has to traverse through the program many times, such commands are very useful. Okay. For instance, I want to print all statements having a given label. The label could be something like CGO or test or whatever, right? So think what all I have to do. From the given program root, get all the functions. So now I'll iterate over all the functions. I have a for loop that iterates over all the functions. Right? So for each function, I will invoke func.getInfo.get statement with label, whatever the label you have asked me for. And then I will say if statement is not null, that is if such statement is present, print it. Done. Now with just these 4 lines of code, I can go over all the functions with all the statements with a certain label. Convenient, right? Any questions?
So what's the unit of the program here? So if you want to like run the compiler across multiple files, how can we do that?
Right. So currently we are taking a single file as the input for this demo. But there is no reason why we cannot handle multiple files also. See, our idea is if we want to work at a high level syntax, we should be able to access different things and different parts of the syntax and traverse them, process them, and so on.
I see. So what is the root here? The program's get root?
So if I'm parsing the foo.i, the grammar says the whole, what should I say, the complete compilation unit is the root. Inside that, I'll have many functions.
Gotcha, makes sense. Thank you.
Any other question? No? Okay. See, yeah, so we already talked about this. So this brings us to the hands-on session 1. The goal of this is something simple. Please open the demo1 project in your Eclipse, and then there are to-dos, a bunch of to-do items. Corresponding to each to-do item, you have to write some piece of code. There is also the sample codes given on top. You can kind of write it yourself, think and write yourself, or if you don't know, you can pick one of the answers and put it here and see that it's working. The goal is, again, parse a simple program, and from the generated IST, we want to print it to a file. And print all statements with a certain label. We can also invoke loop unrolling. Okay? Please open your Eclipse, go back to your Eclipse thing and open your demo1.java. I'll also go there. The instructions are of course there in the Google Doc that I had shared. Okay, let me stop sharing and go to sharing of the Eclipse. All right. So the goal is to go to this demo1 directory, go to demo1.java. You see there are 4 to-dos here, to-do 1, to-do 2, to-do 3, to-do 4. Okay. So try doing these to-dos and we will get back. If you have any questions, please ask. If you are unsure of what to write for these things, there is also the options 1, 2, 3, 4. You can pick and choose and keep it here. That will also work. Any questions so far? Utpal, could you access the VM? Any issues?
Yes, sir. I could access the server. Yes.
Oh, very good. Very good. Okay. See, it's a small group, so we should be able to make it a very much more interactive session. If you have any questions, feel free to ask.
Yes, yes, sure. I'm trying to figure out. I'm not very comfortable with using Eclipse because most of the time I have used Vim and C++.
Sure, you can also try on VI, no issues. But I mean, the Eclipse will make typing many of these things much easier. How about others? Hanjun, how are you doing? Are you able to follow so far? Jay Lee,
I think one of the issues that, at least for me, the resolution is of VPN is pretty low, so I actually cannot read things from the Eclipse screen.
So what you can do is if you go to this demo instructions, instruction F in the demo 0 instruction F, if the VNC quality is poor, there is a way to change it. The instructions are there.
Yes, I tried that, but for some reason from my VNC viewer, there's no option to adjust the, what can I say, the resolution or picture quality. So
Um,
Uh,
I'll
for
figure it
that,
out. Maybe some people have the
screen sharing.
same.
You might
same
want to use screen
experience.
sharing. That's an inbuilt app in Mac OS. Since you use Mac, if
Yes.
you have a screen sharing app, maybe you can try connecting to the server via screen sharing as the VNC client.
Yep. Let me
Here,
try that as well. Thanks.
for that to happen, you will have to disconnect first because we can't have two connections just to.
Right. Right.
disconnect to the server, not the call, not
Oh,
the.
yeah. Yes, yes.
So what I will do, I will start doing the tutorial myself. So I will, for the first to do, we have to get, read the program. So I will read the program using this. So my first to do is done. So what does it do? It reads the argument using the argument, which basically is which has the file name, and then it will print the file. And then I want to get all statements with label test. So for that, what do I have to do? I have to write a for loop that iterates over all the function definitions. So there is a for loop here. I will iterate over all of them. Okay. So in place of 2 root 2, I did that. And then I want to find out if there is a statement with label test. So I did that, that's my, and if the statement is null, I'll print not found. If the statement is not null, I'll keep it. And then what do I want to do? I want to unroll. If it is a while statement, I want to unroll. So first I'll go over all the while statements. How do I go over all the while statements? The for loop is already given here. Okay. And I will unroll the loop. Uh-oh. All right. So I have unrolled the loop. So this is what is my code. So look at the code, right? How simple the code looks. I'm reading I'm going over the full input file, and then I'm getting the AST root. To iterate over all the functions, I'm doing get all function definitions. Then to get all the statements with a certain label, I'm doing get info with that. And if it is not null, I'm printing it. Okay. Remember, there can only be one within a function. There can only be one statement with the label test. Then you see disallows multiple statements with duplicate labels. Now I'm going over every while statement within the function, unrolling it and printing it. Okay. So now I can run this program. Let's hope it works. It asked me to save. Let me save. Right? So it did unroll, and you will see that it also has simplified the code at different places. Okay. So it found there is one statement, G1++. So if we go to this particular runner example.c, let's also open that file. Aman, can you, yeah. So here in runner, there is this example.c. If you look at this code,
this might open it in a different application, I guess, because CDT might not be installed.
Let me see if I force it to open here itself.
Okay. We can maybe open it in text editor and then.
And I'll start sharing the text editor.
Oh, this is the text editor. Okay, great.
Yeah. So if you look at the main code, right, there's a bunch of OpenMP directives, but look at it, there is one statement, test x++. So when we run this demo one, it found this line and also printed it. So I'll go up slightly. Test X plus, it printed that line, right? And it has unrolled the loop. Each while loop, it has unrolled it uh, by a factor of 1. So now the body has doubled. Okay. All right. So now we'll get back to our uh, end of the demo 1. Any questions so far on demo 1? Wow, no questions.
Sir, like in this example,
Huh?
in a while statement,
Uh-huh.
while it's been iterating, it's then inside it's being modified. So, is it the transformation is done afterwards, or how does it happen? Otherwise, it will invalidate the iterator if we iterate.
Very
So,
good.
yeah.
Yeah, Aman, go ahead. Sure, go ahead.
Yeah, Utpal. So this get inherited inclusive will give us a transient set of all the while statements. So this is not giving us a fixed set which we're going to change. I mean, that's one thing. Second thing is, if you notice the nature of unroll loop, it's going to change the structure of the while statement itself. It won't change the set which is being traversed in the for loop at line 40. So it's more like changing the value of an element rather than changing the elements in the set. Does that answer your question?
Uh,
As
maybe
in,
like
as soon as we run line 41 while statement dot get info dot unroll loop one, as soon as this line finishes, the structure of the while statement, the AST under this node while stmt will get updated automatically. I mean, as a result of this invocation, this will not impact any other thing which is there in the iterator that we are going to use in this enclosing for loop. This get
Maybe,
inherited and yeah.
yeah, if I may add to what Aman has said, think of it this way, Utpal. The get inherited enclosure is giving me a list of while statement AST nodes. That
okay,
list is there with me now. Now what I am doing, I'm visiting
it's
each of these and
objects.
traversing each of these while loop nodes and making their and expanding their body.
All right.
That's it. So they are not. So this expansion is not impacting the list I have. Does it
Okay,
make
so
sense?
yeah, that makes sense. And then how do you make sure that the whole analysis information is preserved? Like once you update the while loop, the while
Ah,
state.
very good. Very good question. So that's a my. So we will come to how we stabilize it. So so what you're asking is how is the information stabilized, right? There may be basic
Right.
blocks, there may be control flow graph, there may be points to information, right?
True, true.
Right. So that's something that IMOP does it internally and automatically. We will show towards the end of later in the part of the tutorial how we take advantage of it. The details, the technical details on how it is done, we can share a manuscript with you on how we do it.
Okay, fine. Thank you.
Yeah, thank you. Any other question? No? Let me take a quick straw poll. I mean, among the ones who are participating here, have have you succeeded in getting the uh, getting the Eclipse run, demo 0 run, demo 1 run? Just a yes, no on chat will do. If you say you are not able to, but that's still okay, but we would like to see what's happening. Minesh says he's able to. What about others?
Yeah, I could also
Yeah,
work on.
Utpal could do it. Good. I know, see, this is a very difficult thing, guys. I mean, doing it online. In person, it would have been much easier. right? Um, but yeah, let's try to see that if we keep it interactive, we'll all learn together and it'll be easier. Yi Yuan Wang, how about you? Okay, so if the I'm assuming that the demo one most of you could do. I will now hand over the control to Aman, who will continue with the next part of the tutorial, which is on control flow graphs. Aman, do you want to start right away or give a quick
Uh,
break?
yeah, maybe we can have a break of 5 minutes. Just to make sure that people are not getting overloaded with the concepts. We'll have a short break of 5 minutes, then we'll reconvene.
Yeah, do join back. We will be here even during the break. If you have any questions, please feel free to ask. We'll be happy to take questions. Okay? And though I'm going on mute, uh, yeah, Aman, I'm stopping sharing, so you can start sharing.
Yeah, sure. Thanks. Are the slides visible, Krishna?
Yeah, slides are visible.
Okay.
Aman, you please start in whenever you are starting. I have to restart my machine and join back. Okay? There seems to be some minor issue.
Sorry. Pardon?
I will restart my machine and join back.
Okay, sure, sure.
Yeah, there's some issue with my machine.
Sure. We still have, I guess, 3 minutes for a 5 minutes break. So,
Thanks.
so if any among you has any doubts in the content discussed so far, please feel free to discuss them. So we'll wait for maybe 1 more minute and then we'll restart.
Yaman, I'm back.
Yeah. Okay. So hi everyone. Maybe we'll resume our session now. So as you would have gotten to know me by now, my name is Aman Nogreya. I am a PhD scholar working under Krishna. In this session, we are going to look at how we model control flow graphs in IMOP. The first question is, what's a control flow graph? It is an approximation of how the control would flow among different executable nodes of a function at runtime. It's very useful for various static analysis that we perform during compilation of a program. Unlike various traditional frameworks like GCC and LLVM, IMOP uses the notion of nested CFGs. A nested CFG is a CFG where each node may contain a CFG within itself. So that's the notion of nesting of CFG. Like at the top level, we may have a node within which we may have a CFG, and then the CFG's nodes may again have CFGs within them, and so on. So if you try to relate this to the way we write a program in C or OpenMP, we do have nesting of constructs or nesting of scopes. So this very closely matches the way we write programs at the higher level representations. And that's one of the major reasons why IMOP uses nested CFGs. And it's very useful in modeling the scope information as well. So let's look at a very quick example of a nested CFG for this small code snippet. We have a very small code. We have a function in which in the compound statement, we have one declaration and then a while statement. So here is the control flow graph corresponding to this particular code. If you notice at the topmost level, we have a function definition. This corresponds to main. This function definition is a non-leaf node. We call a node as a non-leaf node when it can contain nested CFGs within itself. So now we see that when control enters a function, there is a certain path that the control will take. That path is represented by the CFG that is contained within the function definition. So for all the non-leaf nodes, we have a begin node and an end node. So these nodes can be used as placeholders. They can be used to, let's say, store information, which we usually store at the entry and exit points of different constructs or scopes. So we can see that within function definition from begin, we will go to the compound statement, which is the body of this particular function. And here in the compound statement, we will see that again, we have a begin node and an end node. The begin node, as soon as the control enters the compound statement, it will first of all execute the declaration int x equals to 0. From here, we'll go on to the while statement. So we can see this int x equals to 0 does not have any nested CFG within itself. So we call such nodes as leaf nodes. Now in the while statement, we'll see that again, we have begin node and end node. Now, as you are well aware of the semantics of while statement, you can verify the control flow here. From begin, we first go to the predicate, which is x greater than 10. If it is false, we go to end. If it is true, we go to x plus plus, which is the body of while statement. And from here, we again go back to the predicate of the while. Once we come to the end of the while statement, we come to its exit point, from which we go now to the end of the compound statement, and from there to the end of the function definition. So this is a very small example which tries to demonstrate the way a control flow graph is represented in IMOP. So there are multiple advantages to the way we represent this control flow graph, which we'll hopefully see in the slides to come. So far, so I mean, now we have discussed what's a non-leaf node and a leaf node. A non-leaf node is a node which can contain other CFG nodes. Every non-leaf node will have an entry point and an exit point, which is called as a begin node and end node. And they define control flow as per the semantics of OpenMP and C. The non-leaf nodes will have the control flow as per the semantics of OpenMP and C. And leaf nodes are the nodes which do not contain any nested CFG nodes. For example, x plus plus or x greater than 10 or int x equals to 0. So if we have any doubts in this slide, I'll wait. Otherwise, we'll move on to the next slide. Okay, so coming to the concrete examples of different types of nodes that we model. So as we discussed, non-leaf nodes can be any nodes that correspond to some scoping. For example, the nesting constructs of C or OpenMP, such as the function definition, while statement, a critical construct, or a parallel construct. All these are different types of non-leaf nodes. Leaf nodes represent the executable nodes in the program, the other executable nodes in the program. For example, an expression statement such as x equals to y plus z, or a go-to statement such as go to L1, or a barrier directive such as hash pragma OMP barrier. So coming back to the example, IMOP will automatically create the control flow graph upon parsing. The line that we had seen regarding parse normalize input, or its variant that we will see later. Whenever we invoke parsing in IMOP, the CFG is automatically constructed, and a dot file is generated at output dump / file name nested.graph.gv. So this will be in the dot file representation, which is a standard representation for expressing graphs in text format. Now the question is, how do we traverse over the CFG? So fine, we have a CFG, but now the main thing is we want to traverse over the CFG so that we can perform some semantic analysis, static analysis on the control flow graph. So we have the two most common methods are getting the successors and predecessors of a node. In order to obtain the successors of a node, first of all, we need to obtain the CFG info object for the given node. So for example, let's pick node n, which is x greater than 10 in this example. On this node n, when I invoke get info, I will get the node info object as we had seen earlier. Then on that, now I invoke get CFG info to obtain the CFG info object. And from here, I simply call get successor. So this will give me a set of nodes which are immediate successors of node n. So in this example, we can see for node n, we have C1, the end node, and C2, the body of the while statement as the successors for this predicate. And similarly, we have get predecessors. Again, we obtain the CFG info object, and on that, we invoke get predecessors. So for example, again, for node n, we can see that the control can flow into node n from either the begin node of file statement, which is C3, or from the body of file statement, which is C2. So we can have we'll have C3 and C2 as the return when node is same as n. Okay. So now moving on to the next topic, which is CFG components. So different parts of a non-leaf node, different semantic parts of a non-leaf node, such as body of any critical construct or a predicate of an if statement, all these semantic parts of a non-leaf node are called as CFG components. For example, in case of file statement, as we had seen, there are four specific components. So for all non-leaf nodes, we have begin node and end node. When we talk about the semantics of file statement, we usually at the higher level view understand that there are two specific components. One is its predicate, which is a predicate node x greater than 10, and another is its body, which in this example is x plus plus. So if you notice, all these CFG components will also be CFG nodes. Now let's look at how do we query these CFG components for a given non-leaf node. So we have various methods predefined in the CFG info object. We'll look at a bunch of examples here. So for example, given a while statement, you just want to obtain the predicate of that statement. If you want to go naively with the help of AST level traversals, you will have to traverse over the various links and the intermediate links to obtain the predicate, obtain the expression which denotes the predicate for a given while statement. Whereas what we are going to propose here is a semantic level query, where given a while statement, we obtain its CFG info object and then directly ask for its predicate. So this is a very straightforward invocation. Similarly, to obtain all the elements of a compound statement. So compound statements are curly braces in C. So we can have multiple declarations and statements in that. So to get the list of those declarations and statements, we can simply invoke get element list. And similarly, if let's say we want to obtain the false branch of an if statement, we can say get cfg info dot get else body. So this will return null if the if statement does not have an else body. So if you have any doubts so far, we can discuss them now before I proceed. I hope these three mini examples are clear on how to obtain different CFG components or the semantic parts of any non-leaf node, such as a while statement or a compound statement or an if statement. Or it can be like critical construct, master construct, or any of the other OpenMP constructs. Okay, so here's a small example on how we perform these queries. So in this particular example, we are doing two things. First of all, we are again using the same method get inherited enclosee on program's root, which is the root of the whole AST that we have passed from the input program. On that, we are obtaining all the while statements which are present in the program. Now, what are we doing with this while statement? For any given while statement, we are simply printing its predicate. We obtain its predicate using get predicate, and then we just pass it to the printer. Similarly, for if statement, we obtain all the if statements, and now we check, do we have an else body or not? So if a given if statement does not have an else does not has an else body, then in that case, we will simply print the statement. Okay, so we'll move on to the next hands-on session now. It's a very small hands-on where we are going to do a bunch of things. First is we will print the predicate and body of each while statement in the program, just like the way we had printed the predicate in the previous slide. And then we have some statement here which says that print the successors of those if statements which do not have an else body. So I request you all to now switch over to your Eclipse screens, and there you will find demo 2. I'll also go over there, and yeah, so I'll stop sharing for the time. Just all right. So I've also connected to one of the Eclipse sessions, and this is the demo2.java. You will find it within source demo, src demo 2. So here you will find a template, and all you have to do is pick one of these 5 options for each of the places, and that will finish our task. So please take some time and try to do it on your own. Let us know if you're having any issues over chat or verbally, whichever mode you prefer.
I'm trying to connect to the server, and every time it's showing the jumbled fonts. It's not.
Oh, so for that, I think you need to set the picture quality. If you'll head over to the instruction sheet that we have given, I think in the first demo 0 itself, you will find a point which explains how we can increase the pixel quality of our picture. So
Yes,
what
I tried
happens?
it. That option
What
is not
happens?
available.
Oh, so you're using VNC Viewer, right?
Yes, I am using.
Okay. So in VNC Viewer, if you'll go to, let me see, properties. If you go to file and then click on properties, you will see something called as options there.
Okay.
In options, you have picture quality, right? So instead of automatic, you can make it high. Most probably that will resolve the issue.
Let me reconnect. Yes, yeah, it is fine. Thank you.
That works?
Yeah, it works.
Okay, great. Okay, so maybe I'll start step by step. Sorry, my speed is going to be slow because I am also connected via VNC. Somehow Eclipse is not working on my system. So over here, what we're going to do is traverse over all the while statements. So if you will look at these options, you will see that option number 2 serves our purpose. Right? So that's about T1. Now we wanted to print the predicate and body. So we can see that we have two print statements here in point, let me check. Yeah, 5 and 1, where we go over different CFG where we access different CFG components of the while statement. So for example, to print the predicate of the while statement, we will use line 5. Similarly, to print the body, we will use option number 1. So this finishes our second and third to-dos. In the next part, we are supposed to iterate over all the if statements, as we can see here. And then in this if statement, we want to check if the else body is not present. So what we require is a snippet in option 4. All right. So now our statement was that if we do not have an else body in an if statement, then we are just going to print it. Sorry, we have to print the successor of that particular if statement. So that comes over here. As you can see, for the given if statement, we obtain its info object, then we go to its CFG info object, and then finally we invoke get successors on that. And whatever is the set of successors, we will simply print that particular set.
Naman, I am not
Yes.
able to get the intelligence working on this because the control key is not working on VNC.
Oh, I think on VNC viewer at the top, you would have an option of Control Alt Delete. At the top of your screen, you will see a specific key for Control Alt Delete. When you click on that, I think the control key will start working on the client. I mean, on the connection. Does that work?
No, it did not.
So the window in which you are seeing the machine's GUI, right? On top of that, you will have a small bar. In that bar, you will see a Control Alt and Delete key.
Yes, I tried it.
Okay. So is it working now?
No, still not working.
Oh, okay. So then maybe just try typing it out.
Yeah.
Okay, so if you have any doubts in these steps that we have performed, please
You may
feel free to
also
discuss.
try the, if you go to, you see, you are able to select the text, right?
Yes.
Then go to the edit, click on edit, you will have copy paste.
Okay, fine.
Oh, and right click would also work, I guess, right?
Right click can also work, I think.
I guess. Okay, so I'll assume that we do not have any doubts in this demo too. Let's maybe spend 1 more minute.
One sec. There are a few new joinees.
Oh,
If you
okay.
are, if you are wondering which sheet we are talking about, what we are accessing, you can join even now. So please go to this. I'm sending you a link. IMOP-CGO, right, Aman?
No, IMOP-VNC, the instructions sheet.
IMOP-J.
/ IMOP-VNC.
Please click there. You can go to the site, uh, download the IMOP client, IMOP sources, open Eclipse and get going. It's so simple. Okay, just if you have any questions, feel free to write. Oh, wait, let me send the link again on the chat. Oh, sorry for that. Yeah, the second one. The first one is in.
Right, so I'll move on to the rest of the session then. I'll stop the share. Okay, so let's move on to, so far what we have seen is how we model flow of control within a particular function. But then our analysis invariably involve various interprocedural queries as well. So let's look at the notion of call graphs. During parsing, IMOP will automatically simplify each call site to one of the two forms: a function name followed by a list of either temporaries or compile time constants. And it can optionally have a temporary, so that x equals to foo of s1, s2, and so on. So this call site is also a non-leaf CFG node. Its name is call statement. Its type is call statement. So let's look at it visually now. So call statement, being a non-leaf node, will surely have a begin node and end node. Now it has two key components. First is a pre-call node. So you can see this block is the pre-call node. It represents the reading of these arguments. So S1, S2 till Sn, all these will be read into the parameters. So that reading is logically represented by the pre-call node. From here, the control will then flow into the called definition or definitions, since statically we might not know the exact target. So from precall node, we go to the begin node of the called function, which is foo. Once the control flow ends, it has to come back to the call statement. So for that, we have a post call node. So from this end node, we come back to the post call node. And this can represent writing of the return value to this identifier X optionally in case if we have one, right? And this dotted line represents so this is more like a data flow edge where we make sure that the local data, data which is local to the caller is sent from pre-call node to post-call node. But for now, let's just focus on pre-call node and post-call node and these edges going to a function and coming back from the called function. So let's look at how we perform traversals on the interprocedural control flow representations or on the call graphs here. So assume N1 and N2 are the names of pre-call node and post-call nodes. So to obtain the successor of a node in such a way that we do go across the function boundaries, we invoke this method get interprocedural successors. So far what we are obtaining with get successors were the intra-procedural successors. So the intra-procedural successor of N1 would have been N2. But now we are going to invoke inter-procedural successors of N1. So we can see that for N1, we have N2 as well as C1 as its inter-procedural successors. When we come to C2, which is the end node of the called function, its interprocedural successor would be the post-call node, which is N2. And similarly, we can see if you want to talk about predecessors for node N2, if we go back, N1 and C2 are the two nodes which were immediately processed before processing N2. And similarly from C1, when we go back, we reach N1, which is the pre-call node. So I hope this isn't too confusing. In case if you have any doubts, please feel free to interrupt. Okay, so moving on. Now, how do we perform queries on this call graph that we have just discussed? So there are a bunch of methods, very frequently used methods. The first one we have already encountered multiple times. So this is more about how do we obtain all the call statements in a given node. Let's say in a while statement, you want to find all the call sites in that while loop. For that, you will say something like miscellaneous dot get inherited inclusive while statement, comma, call statement dot class. So call statement represents the call sites. So we will just give call statement type as the type for get inherited inclusive under the given node. To obtain all the call statements that may target a function. So given a function, now I want to find what all, where all in the program, there might have been a call site which might be calling me, right? So for example, for a function foo, we want to find all the call sites which may have foo as its target. So we have func.getinfo.get callers of this. So quite verbatim here, we want all the callers of this function func. Next, to obtain all the target function definitions of a call statement. So given a call statement, now we may have more than one targets. Let's say it's via pointer dereference, and then the pointer, in the may points to analysis, we may have more than one pointees for the pointer. So when we are using function pointers, we may have more than one targets. So given the call statement, we can find the called function definitions with the help of get called definitions. To obtain the arguments of a call statement. So in a call statement, we have multiple arguments as we had seen S1, S2 till Sn in the previous example. It's a part of pre-call node as I had pointed out. So in call statement, we first obtain the pre-call node, and then on that we obtain the argument list. And finally, to check if a function is recursive or not, this is a very frequently used query. So we have a function ready-made for that. So for that, we simply ask, is it recursive or not? So is recursive is the method. So if we have any doubts on any of these 5 functions, please feel free to discuss. We'll be using them in the hands-on session next.
So for the get callers of this, like are these callers only like explicitly called, or can we have?
So, I mean, they could have been called via function pointers as well. For
Okay.
example, I might have done star p, and then on that I could have made a function call. where P is a function pointer. So since IMOP internally contains a points to analysis, we also take care of the indirectly called functions.
All right. So I mean, it will be conservative, right?
It will be conservative indeed. Being static analysis, yes.
Okay. Okay.
And maybe sometimes in the program, if you do not have the definition of a certain function, then get callers of this will just return an empty list when you
Okay.
are not working at the whole program level, but at a file level, let's say. So do we have any other doubts or questions? All right. So let's move on to the next part, which is the next hands-on session. Again, this looks big, but it's very small. In the first part, we just have to print all the call sites which are present lexically within a given function. It can belong to any of the function definitions. We just want to find all the call sites regardless of the target of those call sites. Second, we want to print all the call sites in the program that may have a given function as their target. For this, there is a one-line invocation that we had seen. Then similarly, for a given call statement, we want to print its target functions as we just discussed and print all its arguments. And similarly, test whether a given method is recursive. So this is just to reiterate what we have just looked at, just to make sure that we are clear with the way we utilize these methods. So I'll stop the share now and I'll go to the Eclipse screen. All right, so yeah, this is the template which is present in demo 3. Please take your time. We'll discuss this after 2-3 minutes, or maybe like a couple of minutes. Okay, so let's start with this. So first of all, we want to traverse over all the function definitions. So as we have seen earlier, we will just invoke the method get all function definitions on the program root, and that should solve the requirement. Then second, we want to find all the call statements which are present within this function. That was the first to do that we had. So we will simply use get inherited enclosure again. It's one of the very frequently used methods. And then we are going to print all the call statements which are present in any given function. Next, so I think the options got formatted just in there. So next was to print all the callers for the given function. So here we can see for the given function func, we obtain its CFG info object, and then we invoke get callers of this. So the reason we are not going to get CFG info is because this is about call graphs, not the control flow graph. Coming to the fourth to do. So given a call statement, we want to find all the possible function definitions that could possibly be the target for the call statement. So for that, we'll just use the first option. And finally, we want to check whether the given function is recursive or not. We want to print that information. So for that, we will just use a simple invocation of getInfo dot is recursive as used in this example, in this snippet. Right, so this finishes our demo. So as you can see, we have done a bunch of things in just a very few lines of code. We were able to iterate over all the function definitions and all the call statements within that function and print the call statement to obtain the callers of a given definition. It's a single line call. And similarly, for whether for the check whether the function definition is recursive or not, we have one line call. And similarly, we have one line call for finding all the call definitions or target function definitions for a given call statement. So if you have any doubts on this, we can discuss them now. Otherwise, I'll proceed on to the next part. Okay, so assuming that we are set with this demo, I'll stop the share and switch over to the slides. All right. So in this next part, we'll look at the notion of scopes, symbols, and types. So there are two kinds of symbols, variables and functions. And each symbol would have some key attributes. So for example, its name. For example, int x, in this case, represents a symbol called as x. Its name is x. Its type is int. Its declaration is that statement int x semicolon. And its scope is the scope where this int x semicolon is present. So there are three kinds of scopes. It could be present either globally at the file level, at the translation unit level, or it could be present within a function, which is a function definition, or it can be local to a compound statement. So, for example, a parameter declaration would also create a symbol, which will be in the scope of function. So for each scope, in order to obtain the list of symbols or a table for all the symbols which are present in the scope, we can simply invoke the method get symbol table. So this will give us a map from set of strings to set of symbols. So for a given name of a symbol, it will give us the corresponding symbol in that scope, symbol object in that scope. So let's look at a small example again. We have this example where foo is calling bar, it's passing x plus y as argument. We have one x defined locally in this compound statement, which is int x equals to 10. Another x is defined again locally, but in the outer scope where we have float x equals to 0.1. So first of all, given this x, one would want to know which symbol is it. Is it symbol at n2 or is it the symbol at n1? So for that, we have a method called as get symbol entry. So at node n3, which is bar x plus y, we want to find what is the binding of this variable x with the symbol. So from here, we will obtain this symbol, let's say sx. And then we have different attributes for this symbol. So for example, when we talk about the type, we can see that type is int. So if we perform get type on that, we will obtain int. Similarly, its name is x. Defining scope is the scope of this if body. And the declaring node, the node which is performing its declaration is n2, which is int x equals to 10. And now let's say we want to go the other way around. Given a declaration, we want to find the symbol which is being declared at that point. We will have something like n2.getinfo.get declared symbol. And this will give us sx back. So I hope these methods are clear. They are quite straightforward, but if you have any doubts, please feel free to interrupt. Okay, so moving on. So this is again a very small demo where we are just doing a bunch of things. First is print the names and types of symbols which are declared in a given function, and then print the scopes of each argument which is passed to a given call statement. So this is demo number 4. I'll stop the share and move over to the Eclipse screen. All right, so this is the code that we have to, this is the template that we have to complete. So these are the options at the top. So the first step is to obtain all the, sorry. Yeah. So first step is to find all the symbols in the given function or the given scope. So here we are moving over all the functions, and there we invoke get symbol table values of that map. So that will give us a set of all the symbols that are present in the function. So we will just paste it here. Now we want to print the name and type of this symbol. So as we can see, we have option 3 here. Then for all the call statement in the program, we want to find what are the argument lists which is present in that particular call statement. So we will go to the pre-call node and from there to the argument list of a given call statement. So note this type simple primary expression. It's a special type of expression which can either be an identifier or a constant. And now, if it is not an identifier, then we do not want to do the next step. Since it's not, sorry, since it's not going to be a variable, it won't have a defining scope. So we have to ensure that if our argument is not an identifier, so we perform this invocation from option 2. If SPE, the argument, is not an identifier, then we just continue from this. Otherwise, the last option being, will print the name of that argument as well as the defining scope of the argument. Sorry, I think it's just the defining scope. So here's our complete code. So I'll go over this again. In the first outer for loop, we're iterating over all the function definitions present in the program. For each function, we're iterating over all the symbols present in that function. We are printing the name of that function, sorry, name of that symbol and its type. Then for all the call statements present in the program, we will iterate over all the argument lists. If the argument is not an identifier, then we continue. Otherwise, if it is an identifier, then we obtain the scope of that identifier. So to obtain the scope of an identifier, we first of all need to find its corresponding symbol. And as we had seen, we use miscellaneous.get symbol entry on the node call statement with the name spe.toString to obtain the symbol represented by the string SPE at that call site. Given the symbol, now we can easily obtain its defining scope by invoking get defining scope. So I hope this is not too complicated. Please feel free to ask if you have any doubts or questions. Do we have any questions here? All right. So this was a quick introduction to symbols, scopes, and types. Now we'll move on to the next topic. I'll stop the share. So the next topic is the environment, or what we call as memory abstractions. So the notion of stack and heap, which is pretty well known and common. There are two main components of any given data environment in case of static analysis: stack and heap. So in IMOP, we term each element of these abstract components as a cell. A stack cell is represented by a symbol similar to what we had just seen. And something new, which is the heap allocation side. So when we do any malloc, each static allocation of malloc or calloc or any of these allocation methods, which can be explicitly mentioned as well, all these correspond to a specific heap cell, which is a memory abstraction or a cell abstraction on heap. And for efficiency, IMOP also maintains a single generic cell object, which logically models the universal set of cells. So this is something very common, which is used, let's say, in points to analysis, where we want to say that X can, let's say we have X equals to foo, and we do not know the definition of foo. At that point of time, conservatively, we will say that X may point to anything of that same type. So in such cases, using a generic cell saves us a lot of memory and a lot of processing time, because it's just a single cell which represents everything else. So how do we perform cell accesses for a given node? So for each leaf or non-leaf CFG node, we can obtain the cells which are accessed, read, and written using these three methods. They are get reads, get writes, and get accesses. Pretty straightforward. So here, let's look at node N1. Here we have star A is equals to 10 plus C plus plus, although this is C. So now you're saying N1's reads are A and C. So as we can see, we are reading the value of pointer A. So it's in the read set. And we are reading value of C while incrementing it. So this is also in the get reads set. When we talk about get writes set, for N1, we will see that C is being written to as a result of this increment. And then, now here is the interesting thing. We are also writing to star of A. So points to information, as I had mentioned earlier, is internally taken care of in IMOP. We can change the points to pass, but there is always an interface called as get points to of a certain element at a certain node, which always has some value. Using that value, we find that A is actually pointing to B. So we'll also get B in the get writes set of N1. And get accesses is just a union of reads and writes. So we'll have A, B, and C here. So if you have any doubts in this example or any questions.
There is one thing I wanted to point here. I mean, these interfaces are the most intuitive. I mean, if you're a person who has to write, say, traverse over parts of a node, right? I mean, call the get info. Okay, I have to get the reads, writes, access. I mean, it's kind of something that we normally use, and having a simple interface can save quite a bit of low-level handling of the code. Anyways, yeah, please go ahead.
Yeah. So the next slide is again a hands-on session. So in case if we want to discuss anything on this page, we can do so. Otherwise, we'll move on to the.
I have a question. So,
Yes.
like if get reads and get writes are they? I mean, can we invoke on any statement or?
Yes,
Like,
we can invoke it on, let's say, a while statement as well. So it will go over all the executable nodes of the while statement and obtain all the symbols or cells which have been read or written to.
okay, so for a compound statement, it will give
Yes.
everything inside.
Pardon?
Okay.
Sorry.
So for a like a while statement, it will give the reads and writes in its body or at the
Full body.
at
So it's a full
At the
compound
control flow
statement.
level. So let's say if you have a function call, in fact, let's say you're calling foo within your while statement, it will also go to the definition of foo and all the possible callees of foo, direct or indirect, and then it will collect everything that can be written. So in a way, it's logically same as saying that, okay, when I am executing this node, what are the memory locations from which I'm going to read? So it's going to be a conservatively correct answer. So it's not just a lexical analysis here. It's going to be a semantic analysis where we actually go also inside the called functions.
Okay. So
Uh,
this is basically giving you like inter procedural analysis, giving you all the information from.
Indeed, yes, yes. So we traverse on the call graphs internally. I mean, these methods internally will use the call graphs that we had seen, and they will do the memorization and other things to keep things efficient. But essentially, they traverse over all the possible things that can get executed within this node, within the given node, and then give us the set of memory abstractions which are read or written or accessed.
Yeah,
All right.
Utpal brought in an interesting point, right? I mean, anyone who has written any analysis will say, okay, give me, I mean, they will manually iterate over all the statements, and then if it is a different type of statement, break over them, and then again get the reads in each one of them. That's a lot of painful work. So even if it's a compound statement, you can do get info dot get reads.
True. It will it will make the life easier of the programmer much easier.
Yes. So in fact, we will see in the next hands-on session that it's very easy to talk about things like data dependencies with the help of these methods. Given two nodes, I mean, they can be statements like a simple expression statement, or they can be function calls and master constructs or anything like that. Okay. So,
Okay.
so we'll move on to the hands-on session now. So here, first of all, we have to write a pass that prints the set of cells in the given expression statement. Let's say we pick the expression statement with label this STMT. Then next we want to write a pass that prints all those expression statements which may write to a given variable. Let us say the name is this var. And finally, we write a pass that for given two statements, let's say with label L1 and L2, determine if they have any data dependencies, ignoring all the array accesses for the time being. So I'll stop the share and we'll move on to the Eclipse session, and then we'll take a short break after this session. All right, so this is across two parts. So in the first one, let's see. So first of all, we want to find the statement with a given label. So if you recall, we had looked at a method long back which was get statement label within a given node. So I'll just take this statement and copy it at 2 do 1, T1. Let me just implement these things. So here we are saying that from the given program, iterate over all the function definitions. Now for given function, find if any statement with this STMT label exists. If not, then we'll continue. Otherwise, let's see what next. We want to find all the excesses which are present in this statement. If it is not a symbol, then we will ignore for the time being. We will continue because this symbol C could also be a heap cell or some of the other cells which are present in IMOP, like field cells and all, which we have skipped for now. Now let's just print the name of the symbol. I'm hoping that's the to do for us. Then we are again going over all the function definitions now. Within that, we will find all the expression statements. And then what do we do with the expression statements? We are going to find the writes which are performed in those expression statements. So again, some very simple invocation here. Node.getInfo.get writes. So this node right now is an expression statement, but it can be any statement or any other CFG node. Again, if it is not a symbol, we will skip for now. Sorry. Otherwise, if it is a symbol, we'll check whether its name is same as this where or not. If that's indeed the case, then we will simply print the particular node. And then we are invoking, we are finding again, similarly, we are going to find the two statements STMT1 and STMT2 with labels L1 and L2. And on that, we are invoking the third part of this particular demo. So here we have to find the data dependencies between STMT1 and STMT2, assuming that one happens before the other, or maybe in parallel, in case of parallel programs. So this one is quite straightforward. There is a snippet of a check. And we also require definition for reads. Okay. So now as we can see, given two statements STMT1 and STMT2, we first of all obtain all the reads and writes that are happening within STMT1 and STMT2. Let's call them reads 1, 2, 1 and 2, writes 1 and writes 2. Now we say that a conflict is detected only if there is, if there are accesses from these statements such that at least one of the accesses is a write. Sorry. So for that, as you can see, we are checking reads 1 overlaps with writes 2 or not, reads 2 overlaps with writes 1 or not, and writes 1 overlaps with writes 2 or not. So this overlaps with is again one of the inbuilt methods. Writes 1 type is a set of cells. So it's a specific type of set, which we call as a cell set. It has its own definitions, especially when it comes to taking care of the generic cell that we had discussed earlier. And it has many other optimizations internally specific to this particular type of cell. So it also has a method called as overlaps with, where we just check whether there is an intersection between writes 1 and writes 2 or not, or reads 2 and writes 1 or not, and so on. So I hope this particular code is quite straightforward and clear. Given two statements, how do we check whether they may access in a conflicting manner any specific memory abstraction? So if we take it one step beyond, in case of OpenMP semantics, if we are able to prove that there is no log taken on that location by these statements, or like while executing these statements STMT1 and STMT2, and if they can be executed multiple threads, then we'll be able to easily declare that that's a data race. And clearly, this is only for sorry, just a minute. Yeah, so this is only for the scalar variables. For the aggregates, like for field cells, like array accesses and all, we have other advanced level concepts present in IMOP, which also handle accesses made across different array elements. So we won't go into that in this tutorial, but you're most welcome to look at the source code and the corresponding code manual and the technical report to get an idea on the same. Okay, so if you have any doubts on this, please feel free to discuss them now. Otherwise, we'll take a short break of maybe 5 to 10 minutes, and then I'll hand over the presentation to Krishna. So I hope these three for loops are clear. The only thing new that we are doing here is invoking get accesses, get name on a symbol, and get writes, and then again printing the symbol. Sorry, printing the node. Okay, so if we do not have any points to discuss now, we'll take a short break of maybe 5 minutes. We'll be around, please. Yes, Krishna.
Maybe 2 hours, right? When we have started, more than that. So maybe let's give at least 10 minutes break. I mean, So they have to
Yeah.
go to the toilet and take water and
Yeah,
they
yeah.
come back.
Sure. Let's have a bio break then.
So
Yes.
it's yeah. So on my watch, it's
It's
9:45.
9:56, I guess.
Yeah. So maybe 9:55 we will meet again. So 10 minutes. So in your watch, set a
All right.
timer. Do come back, all of you.
Yes.
Okay.
Okay, I'll stop this share. I'll be around in case if anyone has any doubts or any discussions, please feel free to come back.
Okay, hey, I have a question. So I was looking back at
Sorry.
demo.
Sorry.
Yeah,
Pardon?
Yeah.
Good.
Okay, yeah. So I was looking back at demo 2, where we identify the successors of the different if statements. And
Okay.
so I saw that, so for 2 of the if statements, essentially the successors return an empty list, right? And so I'm wondering if that's something to do with like the definition of how, or like basically how the successor is defined. Because if I'm looking at the example.c code. And so the
Yeah.
very final, the last couple of lines have this if statement, right? It's like if this var equals 10, then continue.
Yes.
So I would imagine that the successor of this in the, well, I guess the else branch doesn't exist, but basically when it falls through, would be the predicate of the while loop. But instead we get an empty list. So I'm wondering why that is, if I'm misunderstanding something about how this is defined.
No, so if you'll recall, every non-leaf node would have a begin node at its entry. So when we talk about, let's say, the while statement, predicate node will be the second statement to be executed. First one will be the begin node. So the reason why we are getting an empty bracket there is because it's going to the begin node of that while statement in that specific example that you pointed out. So,
Okay.
I mean, does it, uh, maybe I can show you the slides again. Just a minute. Let me go to the share.
Okay. Yeah, so essentially the begin node isn't labeled with an actual program statement. And so
Yes, yes. So begin
the
nodes and
decision,
end nodes, I mean, for now, currently they do not print anything, but depending
right?
upon the requirements, we can like make them appear in any custom manner.
Okay,
So
that makes sense.
from here, like after let's say int x equals to 0, in this case, we would expect the next node to be x greater than 10, right? But for logistics related purposes, we say that no, it's going to be begin node, and that of the begin node is going to be x greater than 10. In fact, we also have some specialized methods which bypass the begin nodes and end nodes. So the requirement that you are stating, that can also be fulfilled by IMOP. Now the interesting thing is I've forgotten the names of those particular functions, but they are also present in getcfg info. So there you will see that we do have definitions where we skip over the begin nodes and end nodes when talking about the successors and predecessors of any of the nodes.
Right.
Does that
So
answer the question?
yeah, I think that's perfect. So just to summarize, like if I wanted to get this behavior from IMOP, I guess instead of calling get cfginfo.get successors, I would, I guess, call something else or write my own routine that also prints the begin as a sort of successor.
Indeed.
Okay. Okay, perfect. Thanks.
Okay, thanks. So if you'll check the code manual or the technical report, you will see a list of other methods which are quite specific to the control flow graph. So what we have looked at are just two methods, I guess, get successors and get interprocedural successors. But we have a bunch of other methods which perform different types of traversals based on specific requirements, like the one you said.
Okay. Yeah, so will this GitHub repo or this Git repo essentially stay around after this tutorial?
Oh, yes, yes, yes. It's public since last year, in fact. I mean, in the
I see.
last tutorial, we had released it. So I'll send you the link over chat.
Okay, that sounds great. Yeah.
If you go to the instructions at the end, in the last line of that set of instructions that we have shared, there also you will find the link to the GitHub repo. I'm sending it to you again.
Great, thanks.
My pleasure.
Yeah, maybe we should resume. Let's start. Let me do this.
I think you have to go to slide 44.
Yeah. Let me do that 1 sec. I will start sharing first. Slide 44. There you go. Start sharing. Now I'm in a, wait, let me go here, start play in the window. Yes, share screen. All right. Aman, you can see it, right?
Yeah, it's visible.
Good. So I want to ask, see, I see there are a bunch of people who are the participants now. And I want to ask, how many of you are not here? See, I mean, those who are not here, they cannot answer. Those, yeah. All right. I'm still assuming that the participants who are silent are still listening. Um, the two participants who have answered a couple of questions, Minesh and Utpal, are you guys back?
Yes, sir, I'm here.
Very good.
Me too.
Very good. Very good. Very good. Okay. How about others? Ahmad, Hanjun, Wang Yan, Yi Yuan, Wang. We have a new participant, Priyanka Ghosh. All right. So let's join back after break. So this is the IMOP tutorial, right? Where we are trying to learn how to use IMOP to do some very cool stuff. Those of you who are familiar with some form of compilation, one of the most common things in compiler is to add some new code snippet. Maybe you're adding a new statement or a new compound statement, or replacing a while with a do while, unrolling a loop, this, that, right? And this is such a common thing. It's a surprise that it happens to be a very complex piece in typical compilers. Okay. See, we need to, if you want to insert some code, you have to kind of build the code bottom up. You have to build the code bottom up in the IR structure of the compiler. If it's an AST, then start building from the leaves, start building the intermediate ones, and do all of it, right? And that can be pretty painful and error prone. IMOP does something much simpler. It says, look, give me the string you want to insert. The program snippet as a string. I will create the appropriate IR. I will insert it for you. Right? So it needs two things. The input, the program string or the program snippet string, and which non-terminal you want to create. An if statement, a while statement, a function, whatever. Right? I mean, here is a simple example. Let's say you want to create a sub I equal to 0 as as a statement inside your IR, inside your AST. Right? Then you have to build an identifier and an expression, which is the index expression. You have to create an array access object. From the array access object, you also need the integer literal. Then you kind of create a new assignment expression, right? And by mistake, you miss something here and there, it's a absolute chaos. Guess what IMOP asks you to do? It says, what do you want to add? A sub I equal to 0. Very good. Just state that. It says, give the string A sub I equal to 0. And you tell it what type of statement, what type of non-terminal it is. It's a statement. So you pass the statement dot class. You pass these two as argument to a static method called parse and normalize. Voila, it's done. So it creates the appropriate AST for you. I mean, look at another example. Let's say you have been given a while loop. You have been given a while loop. And our goal is to unroll the while loop. What do you mean by unroll? So I have a while loop, predicate, and the body, right? So I want to kind of, in the body of the while loop, I want to duplicate the body with a condition check in between, right? So let's do that. So the way IMOP does the unrolling is trivial for anyone to read it, right? So first I'll take the while loop, the loop variable, and invoke the getinfo.getCFGinfo, and then I'll say, hey, if I unroll, what will I have? It will start with a while, then the predicate. What will the predicate be? Same as the predicate of the while loop. So I'll do cfginfo.getPredicate. Close parenthesis, close bracket, open parenthesis. Then the body of the while loop plus a condition check. What's the condition check? If the while loop predicate is false, then break. Followed by while loop body, close parenthesis. Think about it. Can it be anything simpler than this? No, right? I mean, this is how we learn an unrolled loop body. Now you take this snippet, this string, create a new body. You create a new statement, which is a while statement. You don't even tell it's a while statement, just it's a statement. You do front end dot parse and normalize the string and the dot class. So you have got in a compound statement, there may be some additional curly braces here and there. So you say, okay, you invoke this function called compound statement normalizer dot remove extra scopes. Okay, if you want, you can do that. By the way, we got the new body. We have not yet replaced the loop with the new body. We have gotten a new body. We have to insert it. We will see how to insert it in the demo. Right? So if you look at it, we are saying we really don't worry about we really don't worry about the exact bottom-up construction. What we are doing, we are creating a new loop. That's it. Aman, correct me if I'm wrong. If I take this new body, I've created this new body. I don't have to insert it, right? I can keep it as it is.
Yeah, we can keep it as it is. We can print it if you want. And like,
we can print it, and I can also replace it, right?
Yes, we can replace it as well.
We can also replace it. So now, if you look at this particular code, right, guys, this code is what we study in the compiler textbook of unrolling, and that's pretty much is there here, right? Okay. So we created this thing. We created the loop, and then we invoke the parser. This parse and normalize, what it does the parsing for you. Now you may wonder, what if the string I have is not a valid string? what do you expect it should do? It should throw an exception. That's what it will do. Okay, most intuitive. Okay, any questions on this? No?
I have a question.
Yes.
Yeah.
Please go ahead.
Yeah. So I just wanted to know what kind of internal representation does IMOP use to,
AST.
yeah,
It's an
have
AST.
a,
Abstract.
okay. So,
On top of
so
it,
this AST, yeah.
on top of it, CFG and many other things are built on top. But the underlying thing is an AST.
So is it like reused from open source like LLVM or something similar to that kind of representation, or there is something added on top of that, like
See,
additional information?
no, yeah, so
Yeah.
we do not actually use a low-level IR like LLVM. It's a high-level AST. And the reason is we want to stay at the high level, very high level. It's easy to reason about uh, annotations like OpenMP annotations at a high level.
So then how do they handle this what you call error handling and all when it is at that level without this lexical syntax analysis and all?
Oh,
So
that is
how does this IMOP handle that kind of, yeah?
so. Indeed, when we call this parse and normalize, it will read the tokens. It will build the parse tree and give you the AST for you.
So, Ahmed, in fact, the exact grammar is
Yeah.
present in the repository. It's very similar to the grammar that we will read in, let's say, the ANSIC or ISOC standard, as well as the OpenMP API. So, what we do is use Java CC and JTB to, I mean, what we have done is use Java CC and JTB to create a parser from the grammar at the higher level of representation. And then that's the AST that we obtain. And on top of that, as Krishna pointed out, we have multiple other representations at the higher level semantics. For example, concurrency analysis for OpenMP programs. So those relations are also modeled on top of the AST. So, I mean, that's our overall framework. Does that answer the
Okay.
question?
Yeah. So actually, I had been working on this AST. So it is like what you call. So I was thinking something like the GCC AST where they put this expression and what you call the tree format which they put. So
Okay,
I
no, so
was
there
actually
are certain
to relate to that.
differences.
Yeah.
Okay, no, so I mean, the main difference, as I just pointed out, is that AST is the base representation. We never actually work at the AST level. For example, in this code, you would not see anywhere references to the fields of, let's say, the statements, right? Like we are saying things like get body, get predicate. So these are higher level, slightly higher level semantics than what we will obtain when we are working at the AST level. So
So are you able to dump that kind of information? So that is my actual
can you give an example of
the
like what
representation
type
that
of
you put in. Like in
can you,
LLVM, we can do like dump AST and we get that entire structure.
yeah,
Like how?
yes, yeah, we can do that. We can
Yeah.
do that.
Okay. Okay.
So Ahmed, I mean, let me.
Yeah.
If you are familiar with LLVM and GCC, think how if you have to insert some statements, right? Uh,
Yeah.
you have to build it bottom up, isn't it? You have to build every node and then join the nodes, create a bigger node, make a state from the individual identifiers, make an expression, from the expressions, make a statement, from the statements, make a compound statement, taking the predicate and the compound statement, create the while statement, while loop, things like that, right? So there you have build bottom up. And what IMOP
Yeah.
does is trying to save that headache.
Okay.
Makes sense, right?
Yeah. Right.
Yeah.
Thank you.
Yeah, thanks for the
So
question.
Ahmed, please feel free to contact after the session in case if you have any other specific doubts regarding the features that are provided by IMO in terms of representation.
Sure.
Okay.
Thank you.
Thanks.
All right, fine. So besides these things like unrolling, I mean, working at this, I mean, working at this level where you take the string and generate the uh, AST, which is pretty handy for adding code in the middle of uh, my program. IMOP also supports this notion of elementary transformations. Okay, so as it's built around that lot of things. See, the different parts of non-leaf nodes, right? Such as in a while loop, you have you have different components. So the non-leaf node is a while statement. So now it has many subparts. You have a begin node, you have an end node, you have body, you have a predicate, right? So these are all CFG components. Okay. So we do support different elementary transformations. For instance, if you have a while loop, while statement, I can have elementary transformations like set the predicate, set the body, and so on. Okay, that will help us kind of change the predicate if we want, and so on. We can add a predicate if you are building it one by one step, and so on. So, for example, if while statement is pointing to an object of while statement in the AST, basically while statement is pointing to an AST node, which is a while statement. I can do while statement dot get info. That will give me the info object. Get the CFG info, and then I can do hey set predicate. It will change the predicate. Okay. Here is another example. I want to add an empty else body to the if statement if none exists. Why am I doing it? Maybe I'm trying to normalize, or maybe I'm trying to add an else body, or maybe I'm creating an if statement. I've already added the if, adding the else. There are many reasons, right? So now this add empty else, what does it do? It takes an if statement as an argument, right? So I'm taking if statement. Whatever I have to do, let me do a get info. Do a get info and then get CFG info. And on the CFG info, I'm checking, hey, does it have a else body? If it already has else body, good, let me return. Else, let me create an empty else body. What is this empty else? It's a curly brace, right? So I will do front end dot parse normalize curly brace statement dot class. It's a compound statement, no statements with it, no problem. Then I will do CFG info dot set else body and set this string. Sorry, set this statement. I mean, many times when you write your own compiler passes, you do want to add these things. And what IMOP tries to do is to provide an interface by which you can do it in the most simplest manner you can think of. Okay, I want to add a else. Create an else body, just attach it. How to create an else body? Invoke, parse, and normalize. Okay. Let's go on to hands-on session 6. Here our goal is to do two things. Write a pass to perform loop unrolling for while loops. We already seen the code more or less. We need to do that. Second, translate a do while loop to a while loop. In normally compiled books, we see that we want to transform while loop to do while loop. That can also be done. In this example, we will do the other way around. Do while loop to a while loop. Okay. Please open your, what should I say? Please open your Eclipse project of IMOP. For those of you who have joined late, uh, feel free to follow the instructions. Aman, please paste the link once more in
Yeah, I'll
it's
send
also
you
there
the
on top of the session. The bit.ly link is there on top. Okay.
I'll post it as in case if you have to switch over to the setting Eclipse setting.
Okay. This is demo 6. Those of you who are following along, please open demo 6 dot the demo 6 project and the demo 6.java, and let's get going. Okay. I will start working on the demo after maybe a couple of minutes. All right. So now what we will do, we will I will open my Eclipse window. Okay, let me stop sharing here and open the Eclipse Eclipse window for sharing. Screen Eclipse. So what I did while I was waiting is to add some comments on top of this demo 6. So I've opened the IMOP compiler. In the IMOP compiler, I'm in the SRC directory. There's a demo in the demo 6. I'm in demo 6.java. The first target is to unroll a while loop, right? So now I want to, so I look at the ones I am shouting in capitals. Okay, so that's what I want to write the code for. For each while statement in the program, what do I do? So I have a for loop and I want to fill in the to do. So I have a for loop already here. I will uncomment it and there I will fill in for each while statement in the program. How do I get? I will call our favorite get inherited enclosing function. Okay, so it gives me all the while loops. Okay, it says give me one more curly bracket. Fine. So now, wait, let me. Just a minute. Okay. Let me move this guy down here. Okay. So what did I do? I wrote a while loop to iterate over all the while statements. Once I have the while statement, I want to get the predicate of the while loop. Okay. So let me, so this will be my code. That is my to do 2. I got the predicate. Similarly, I get the while body. Okay. Then I want to create a new while loop. How do I create a new while loop? Um, See, like we discussed before, new while loop will have, it will start with the while predicate, then the while body once, then checking if the condition has become false, if so break, else while body, right? So that is my new while loops body. I'll just create it. So that's my string, okay? And once I have that string, I can use that string to build a new while statement. How do I create a while statement? Using our newly learned function, new while statement equal to front end dot parse and normalize. Parse and
Krishna, the font is quite small.
font is too small, is it?
Yeah.
Okay. How do I make it? Does
Yeah,
anyone
this is
know?
good.
Oh, this is better, is it?
This is good. Yeah.
Oh, you're saying keeping the window small is a good idea. Okay. Okay. And now what I will do, I will replace the new while statement in the uh, body of the program. How do I do it? So I got the new while statement. I have inserted it. After inserting, I'll say, hey, there may have been some additional braces, remove them. I can, of course, now print the whole program. Okay. I can run this much code. This should be fine, I hope. We save it. Error exists. Oh, wait. Demo 6A. I have to. Is it uncommented? No, right? Oh, sorry.
Line
I
32.
Yeah. It's my bad. I forgot to. Okay, now it should. Yeah. See, it unrolled the loop. Look at it, the while loop has been unrolled. Whatever the old while loop was there, that's not so important for us. Okay. So now look at this do while statement here, which is again part of my program. Okay. Now I want to change this do while loop to a while loop. If I want to do that, what I will do, I will first traverse over all the do while statements. That is as simple as just writing a for loop. That is simply writing a for loop which will call get inherited enclosee with the program root and what type of statements I'm looking for? Do statements. Okay. And now what do I want to do? Look, I want in the do statement, there is a predicate and there is a body. Let me get those two. Let me get the predicate. Let me get the predicate and then let me get the body. Once I have these two, once I have the predicate and body, what do I have to do? I have to build a while loop. Now, those of you who know any C, Java type of languages, right? If I have a do while loop, I want to convert to equivalent while loop, then I need to get the body of the while loop executed once unconditionally. That's what I will do. Ouch, I got the wrong thing. Wait. Where am I here, right? Yes. Okay. So I will get the a string, the while string as, what does it have? The do body followed by the while predicate followed by do body. And then I'm putting all of these inside curly braces. Why am I putting all of this inside curly braces? Just to be safe, so that there are no single statements which are remaining. We can always remove the unnecessary curly braces at the end by invoking something like remove extra scopes. Okay, so I got the new while string. Now what do I have to do? Take the while string and create a while statement. Okay, I can create the while statement. And what do I do with this while statement? I will replace it. I will replace it by calling replace nodes. Okay. So what I can do after I do that, I will say, hey, please remove any extra spaces, extra braces. Okay. I can see, this is something that you will find handy. Instead of dumping the whole file, which can be pretty big, right? Sometimes you may want to just print this AST node or just dump root, but to a specific file of your choice. So here we are doing dump snapshot, dump root to a file called foo-do while, something like that, whatever your call. Okay. You can also write to the standard output the complete this thing. See, this can be inside the while loop, inside the for loop, which will dump these things for every do statement, or you do it only once. Let's do it only once. That's more reasonable, I think. So we'll do it only once. Okay. So what did we do in the do while? We took the do while statement. From there, picked up the predicate, body, and then created a while statement. How did we do that? Created a string and then simply called parse and normalize. Okay. So now if we run it, let us see, I hope we are not introduced to any bugs. Now look at it, the do while loop that we had seen has been converted to a while loop. But look at it, before the while loop, the body of the do while loop has been repeated. Cool, right? Any questions? No questions? See, if it is normal face-to-face things, right? We could say, if you ask a question, I'll give you a chocolate. Unfortunately, I can't give you chocolates. What is it? Okay. The chat window. What is this, Aman? What is this T1 colon 3, T2 colon 4?
Oh, those are just the mappings. To-dos have
Oh,
numbers.
oh,
I'll
oh,
do it for verification.
oh, okay. You are helping more. Okay, good. All right. So if you are fine with this, we will go forward. Let me know if everyone is fine with this. Utpal, could you try this? Did it work?
I I could not, but I think I got the intuition.
Okay, very good. Very good.
It looks really neat.
Okay, good.
There's some internet connection issues. Like while I type it, there's a huge lag between the
Yeah, yeah.
characters.
Okay, okay. Fine, no problem. Okay. Anyone has any other question? Now? Okay. So what we have learned so far is how to uh, build AST nodes using a very simple interface. Let me start sharing my slides again. Okay. We'll continue with our discussion of this and look at this way. There are many times when we want to do transformations like this at a higher level. For instance, say I have this while loop. Okay. Don't ask me what it does. That's not so important at this time. Assume that we want to add something simple. This RB you see, right? I want to know every time this RB is read, I want to do something. Okay, I want to add what we call as a read barrier. You would also do something like whenever certain variable is written to in the program, do something. Right? To add such a read barrier, think if RB, where all RB is read at line number 2, RB is read at line number 3, right? To add a read barrier before line number 2 is easy. To add a read barrier for the access of RB in line number 3, can you think where all I have to add the read barrier? Right? Think about it. While you think, remember to do this read barrier, we have to do two things. We need to keep in mind what to write in the read barrier. That we know. Okay, I want to, let's say, keep a log of how many times RB is read, or write to some log file, or kuch bhi. I can do something, any of that sort, right? And then I need to find out where to insert this snippet of code. As we said, line number 2 is straightforward. Line number 3, where all do I have to add? Anyone wants to try where all I have to add the read barrier?
We will send a virtual chocolate if you tell us the number of places where we have to insert it. Whenever we meet ever in life, we'll give the chocolate, then it will be like a rain check.
Yeah, Utpal, you're saying something?
No, sir.
Okay.
I'll
Yeah,
just-
anyone can think where we can add the RB. Look, I cannot possibly add this code inside the while loop always, because the read barrier could be arbitrary code. And inserting that code inside the predicate is going to be a pain. Right?
So maybe before if.
So we have to add once before the while loop and once at the end of the while loop. But here there are two continues. So I have to, if you look at it, the while loop, right? The while loop's last statement executed is line number 6 or line number 9. So I have to add a read barrier before line number 3, one just before the continue at L1, one before the second continue at line number 9. Ouch. I mean, now I have to kind of, if I want to add such a write barrier, I have to manually find out every such place and insert. Right? Just because I cannot insert the read barrier inside the predicate. Right? Pain. And the worst part, it can be error prone. There are times when you will miss a few. Okay.
And
So,
just to add one more thing, Krishna, which I think I forgot to add to the slides. A minor thing here is that we need to keep in mind that we won't actually know the code that we are going to process. At the time of compilation, we'll have to think about all the possible cases which could be present and then take care of all of those cases. Like in this example, we can look at the example, a concrete example, and then we have to find where do we need to insert the barriers. But in practice, we actually won't even know what's the program. We'll just have a while statement in our hand or a certain read or a write node in our hand. And then we'll have to think about what are the possible scenarios where we would have to insert the nodes or the barriers, read barriers.
Yep. We can have even a complex expression statement like GCC allows, right? So I mean, many such possible cases which we can't imagine easily. It's best automated. So what IMOP does is it says, look, it gives 5 CFG transformations. What are those? Insert immediate predecessor. So I can add some code, which is basically AST node, before a predecessor. Insert immediate predecessor. I can kind of make this node as an immediate predecessor, as an immediate successor. I can insert something on an edge. I can remove a node. I can replace a node. Okay. What's the advantage? This is completely hiding the syntactic forms of the nodes that are involved in the process, whether I'm inserting in the middle of a while predicate or in the middle of a complex expression, doesn't matter. So I can do something like, if I have this RB here at line number 3, I can just do some simple code like this. Insert immediate predecessor dot insert node, where node is this RB node, comma instrumentation code. So I'm talking about the RB of line number 3. At this AST node, I will say I'll just do insert node comma instrumentation code. That's it. I don't need to go and manually insert it. IMOP will do it for me at the appropriate places. Okay. Those, any one of you have tried adding code, you will know how painful it is in a compiler, because we may end up adding it in the middle of an edge or at after the basic block. I have added something, but it fell after the basic block and things like that. So here, IMOP takes care of all that. Okay. That brings us to the hands-on session 7. Aman, can you run us through this? And from there take over?
Yeah, sure.
Thank you.
Yes, sure. I'll do.
So
yeah, so hi everyone. I'll maybe share the screen from my end. That way I'll have the control. Actually, before that, I'll just go over the. I mean, this slide first. Then I'll share my Eclipse screen directly.
Sure.
Okay, so in this particular hands-on, as we can see, we have to write a pass, which will. Sorry. Yeah, sorry. So in this particular session, we'll have to write a pass which will instrument a program such that immediately before write to any scalar variable named as this where a notification is displayed. So this can be any printf message. So first step in this particular case, as we had seen in the last few slides, will be to detect what all CFG nodes are going to write or may possibly write to the variable this where. Second is to create a notification message as we had done earlier, creation of nodes. And then third will be to finally insert the newly created statement immediately before the detected node or nodes. So now maybe I'll switch to the Eclipse screen. Krishna, maybe we can close the share now.
Yeah, let me do it. Yeah, I've stopped sharing. So after maybe a couple of minutes, whenever you're ready, you can take us through.
Yeah. So maybe I'll start I'll start working on this hands-on side by side. All right, so I'll quickly go over this code. So first to do was to fill the iterator set. Here we see get lexical CFG leaf content. So this is a certain method which helps us obtain the lexical contents of a CFG leaf node. So for example, if you have a while statement, then this method will go inside the while statement lexically, not go to the called functions, and collect all the CFG leaf nodes which are present within the bounds of that while statement. So we are using that function here. We will go over all the function definitions of the program root. For a given function, we will find all its lexical CFG leaf nodes. Then we are going to find what are the possible writes that may happen at any given CFG leaf node. If it is not a symbol, we will continue, we'll skip for now. Because what we want is a symbol with the name this where. So if the symbol does not have the name this where, then we will continue again. So by the time we reach line 43, we now have a node with the variable node, in fact, which actually has a certain right to, which may write to the symbol with name this where. Now all we need to do is create a certain message. So for example, our message is about to write to this where, and let's say it's just a printf message. So we will just create a string, and then from the string we'll again use the method. We'll again use our parse and normalize on line 45. We'll pass new str, parse it like a statement. Once we have the statement, now we have to insert it before the node. So now, as you can see, it's a very straightforward call, regardless of what the node is, whether the node is a predicate, whether the node is like any of the expressions of a for loop, or it be even a predicate in the num threads clause in case of a parallel construct. It can be any kind of leaf CFG node. Regardless of its kind, we'll just use a single line invocation. So we'll say insert immediate predecessor, node comma new statement. So for the node, insert a new predecessor called as new STMT. So this will take care of all the syntactic sugar, including even labels and different constraints that we have when we are writing code at the higher level language. So I hope, I hope this particular demo is clear. Please take some time to go through it once again. And in case if you have any doubts, we'll discuss that.
Can you once more
Yeah.
explain line number 35, why we go through the...
Sorry.
Yeah, just line number 34, 35.
Oh, okay. See, the reason why we are going over all the leaf nodes is because we do not want to process any node more than once. So let's say if I take a non-leaf node as well as a leaf node, or let's say if I try to find all kinds of nodes, the problem would be since we're talking about nested CFG, I might take a while statement and then process it, and then I might also take predicate in that while statement and process it. What we actually want is an insertion just before the read or write is done. In this case, a write is done. So when we want to talk about the immediate point preceding a certain axis, we should always be looking at the leaf nodes and not the non-leaf enclosure of those nodes. So that's the reason why we want to find all the CFG leaf contents. The reason why it's lexical is because we are anyway moving over all the function definitions. If I do not keep it lexical, then because of the cross invocations, we might again do the mistake of performing the instrumentation more than once. So that's the reason why it's lexical and why we are talking about CFG leaf nodes. I mean, this is one way. There might be, I mean, there must be other ways in which we can obtain all the leaf contents, but I always find this to be one of the easiest ways in which we can go over all the executable nodes, which are not the non-leaf nodes, and then do some processing on those nodes. Does that answer your question?
Yes, yes. I think that little bit like the way we see CFG normally is a little bit different. So that's why I mean the confusion is here because of the nested CFG.
Yeah, I guess it takes some time to get used to it, to be honest. But then once you're used to it, you will realize it's actually very convenient to look at it this way. Because at the higher level abstraction, if we try to flatten out the CFG, what we will obtain will be essentially similar to an IR level representation, IR level representation. And at that representation level, we will lose a lot of information regarding the scoping, which is very much important, as I hope you would have noticed in
Yeah.
all these demo sessions. So it does take time, but I guess once you have written a bunch of lines, I guess you'll get the feel about how exactly to think when we talk about these nested CFGs. And from my personal experience, like I have written some code in LLVM and ROS compiler frameworks as well. So from what I can say, being biased, obviously, from what I can say is that this I feel is much more convenient as compared to going to the low level of representations for most of the analysis and transformations that we require.
Yes, yes. I completely agree. Like working at low level is very difficult. Mostly,
Indeed.
specifically
That's,
for high level transformations.
indeed, indeed. Like for example, if you want to do something like register allocation, IMOP doesn't go to that level of the compilation. So yes, we do not take care of that, but we do take care of everything related to semantic analysis at the higher and mid levels, like data flow analysis and all.
All right.
Okay, so in case if we do not have any other doubts on this or questions on this demo, we'll move on to the presentation. I'll stop the share. Okay, so now let's move on to the third letter of IMOP, which is OpenMP. So it has been written with OpenMP semantics in mind since as early as its design phase. I mean, before we even thought of creating IMOP, our requirements were quite clear that we want something specifically for OpenMPC, something which is easy to use. Hence, all the program abstractions, starting with the CFGs and CGs and all the data flows that we model, they all preserve the semantics of OpenMP. Especially for data flow analysis, IMOP in fact provides a framework where we have an abstraction. In this abstraction, the compiler writer need not provide any information which is specific to the OpenMP semantics, but only the information which the compiler writer would have provided in case of any CL compiler, like LLVM or GCC. With only that level of information, IMOP then internally and automatically convert those serial semantics to OpenMP semantics. So that's something which is again, which reduces chances of many bugs, and it reduces the complexity as well. Like someone can write an OpenMP conforming analysis, even if the person doesn't know anything about OpenMP or parallelism to begin with. So there are multiple new program abstractions as well as some existing program abstractions which are already present in IMOP, such as concurrency analysis, log set analysis, and so on. So we'll look at, first of all, the intertask communications. So for those who have gone through the OpenMP API or the key parts of it, I'm sure they would remember that communication across different tasks or threads in OpenMP is allowed only if these 4 events happen in order. First is that the thread T1 writes to a shared location, say x equals to 3. This has to be an atomic, right? Then second is T1 flushes that location. So x equals to 3 will be then flushed. So there is in fact a flush at the end of the atomic block. Then T2 must flush that location so that it can capture the information from the main memory to its local copy. So the value of x equals to 3 is now visible to T2. And then T2 is going to read from that location. So let's say it's printing x. So we can see that with the help of these 4 events in this order, in this particular order, interspersed with maybe some other events, not related to variable x, we can see that thread T1 or task T1 can communicate with thread T2 over the OpenMP memory model. So we model these communications. So like modeling these communications is something which is very crucial in order to ensure that the semantics of OpenMP are preserved. So we model these communications by creating something called as intertask edges, which are edges created between 2 flushes where such a pattern exists. And once we add these edges to our control flow and call graph edges, what we obtain is a super graph where we can essentially assume that it's a serial program and then do the processing of data flow analysis. I mean, it's not as simple as, I overly simplified it, but that's the gist of the notion of intertask communications, that these are just the extra communications and the only communications that are possible as per the OpenMP semantics. So let's look at concurrency analysis, one of the very commonly used abstractions. So as you might recall, a barrier is a program point where multiple members of a team, multiple threads in a team will wait for each other until all the threads have reached that particular program point. We define a phase as a collection of those statements that lie between any 2 consecutive set of barriers. So let's say there is a barrier B1 where all the threads have synchronized. Now from B1, there are multiple paths which can go to B2 and B3. So B2, B3 will become another set, and all the statements between B1 and B2, B3 will become the phase, one phase. And it's easy to understand that if 2 statements do not share any common phase, then they can never run in parallel. Because for them to run in parallel, there must be a phase where one thread is executing one statement and another thread is executing another statement. So this observation, which is the main logic behind concurrency analysis, it helps improve the precision and efficiency of static analysis of various parallel programs. And IMOP provides various interfaces using which we can perform queries on this analysis. So let's have a look at some of them. Now, let's say if you want to obtain all the static phases that are, static phase is same as a phase. So if you want to obtain all the phases that are present in a parallel construct, we have a very simple method called as get connected phases. So parallel construct dot get its node info object, and then on that invoke get connected phases. That will give you all the phases which are present within that parallel construct. Then to obtain the set of statements that may belong to a given phase, we just need to invoke its node set object. So we'll invoke dot get node set on that particular phase. Similarly, if we want to find all the barriers which may end a phase, we say ph dot get endpoints. Similarly, for those barriers which begin a phase, we say ph dot get begin points. And to obtain all the phases in which a statement may run, it's the other way around. So like a statement may be a part of multiple phases. For example, if it's in a loop, that particular statement may be encountered in the context of various different phases. So if we want a set of all those phases, we can go to the node phase object, node phase info object of that statement. Sorry. and then invoke the phase set method over that node phase info object. So for the purpose of a tutorial, so wherever we find abstract phase question marks, we should treat it as a phase. So this abstract phase is a superclass which can be defined by any of the different definitions as per different concurrency analysis. So for our purpose today, we will just assume that phase is the only implementation of abstract phase. So with this in mind, we'll move on to the hands-on session. But before that, if you have any doubts regarding what exactly is a phase or what are these methods, then please feel free to ask.
Yeah, so I have a question related to what is a phase? Is it an integer or it has it's kind of an node? I mean,
It's an object. It's a Java object which has multiple elements in it. So one is the set of barriers which started that phase. Second is what are the reachable statements from these barriers on the barrier-free paths. So those are called as the nodes in that phase. And third is what is the next set of immediately next set of barriers which were encountered when we started with the starting barriers. That's called as the endpoints of the phase. So these three are the key components of the phase. And obviously it has a phase ID as well to distinguish it easily with other phases. So the logic here between behind a phase is, let's say you have four threads, and they are waiting at two barriers, B1 and B2. Their wait is complete. B1 and B2 synchronize with each other. Now from these barriers, when we move on to the next set of barriers, let's say B3 and B4, the statements that are encountered in between these two, B1 comma B2 and B3 comma B4, all these statements will form one phase. The reason why we are modeling it this way is because now we do not have any clarity on what will be the order in which these statements will be executed. I mean, even if we are taking logs or atomics on these statements in a phase, we do not have much idea about what's the order in which the statements will be executed in general. So does that clarify the notion of a phase?
Yes, yes. And to get these endpoints and all, we need to do some analysis on top of, I mean.
No, so there is an analysis which IMOP already performs internally. We can also add other analysis. So when we perform something like get endpoints, it will run a certain MHP analysis or a phase analysis internally, and then it will provide the result as given by that analysis. In fact, that's the reason why we have a superclass called as abstract phase, where the first question mark is the type of begin points, second question mark is the type of endpoints. And what we are looking at is one specific instance of that abstract phase, which is a subclass called as phase with a capital P here. So we can indeed implement our own concurrency analysis, but IMOP provides a base analysis, which is conservatively correct. So that serves our purpose. Like in case if I do not want to add a concurrency analysis on my own, IMOP will take care of it behind the scene.
Okay.
Okay, so now let's move on to the hands-on session. So hands-on session 8, let me go over this quickly. So what we have to do is something very simple. We have to print the number of static phases which are present in any given parallel construct. We have to print the highest number of statements in any given phase. And then we have to print the set of all the CFG leaf nodes that may run in parallel with the given expression statement. So I'll stop the share and move to the code. So in the interest of time, and since most of you might be tired by now trying all these demos, maybe I'll just directly show the final code that we will write to achieve this particular set of to-dos. In case if you want to not look at the screen and try it out on your own, please feel free. All right, so this is a very small code. Let me just go over it quickly. So we find, so get exact inclusive is something similar to get inherited inclusive. We can skip the differences for now. So for some reason I've written exact.
I'm not.
Sorry.
I'm not able to see your screen. Maybe you missed to
Oh, sorry.
share.
So yeah. I forgot to share. Sorry. Thanks. Okay. I hope it's visible now.
Yes, it is.
Okay. Great. Yeah. Thanks for that. So now looking at this code, we are just going to find all the parallel constructs within a program's root. We are using this method get exact inclusive. It's only for efficiency purposes. It serves the same purpose as get inherited inclusive. We can refer to the documentation later. Now, once we obtain all the parallel constructs, what we want to find is all the connected phases within that. So as I had mentioned earlier in the slides, we can just invoke its node info object and then call get connected phases in line number 30. That will give us a list of all the phases, and then we'll just print the size. That will give us the number of phases in that particular parallel construct. And then later we want to find the highest number of statements in any static phase in the system. So we do a very simple calculation here. Max is 0. We take each phase one by one. Now what we want is the size, the elements of that particular phase. So for that we obtain this get node set. We obtain the set with the help of this method get node set, find its size, and then see which one is bigger, and then allot the bigger size to max. Once we iterate over all the parallel construct, we will now in max have the number of statements, highest number of statements within any phase in any of the parallel constructs. So I guess the key functions here to note are get connected phases, get node set of a phase, just these two. And now let's go to the third part. Here, so we have to print the set of all those statements that may run in parallel with the given statement. So now this is something interesting, right? Like, because in OpenMP, let's say you want to safeguard certain reads and writes, and you want to check whether a certain category of statements may run in parallel with the given statement or not. And when I mean to say in parallel, I'm assuming that we do not have any locks on them. Obviously, that's not a correct assumption. So we also have the log set analysis, which we are not going into we are not going into the details of log set analysis right now. So for the time being, let's just assume that the meaning of running in parallel is that if two statements share a phase, then they may run in parallel. This is an incorrect definition, but I think it should suffice for the purpose of this tutorial. So here, we just go over all the expression statements in the program. Let's say it's exp Now, all we need to do is get all the phases of this expression statement. So we say get info, get node phase info, get phase set. Once we have that, then we will print all the node sets of all those phases. So I hope this logic is clear here. We get all the expressions one by one. For all those expressions, we find all its phases one by one, and then we print all the nodes present in those phases. So there will be repetitions here. We can instead take a set and then print the set later. But I hope the idea is clear. Okay, so if we have any doubts on this, okay, so I'll move on to the next part, which actually is also, sorry. So next slide is also a hands-on session. So maybe I'll leave this as a homework for you all, because I think we need to cover up the rest of the slides first. Maybe we'll come to it after the session. If you're interested, we can discuss. So I'll directly go on to the other key features of IMOP. So for now, the demo sessions are over. So you guys should feel relaxed now. Okay, so let's look at some of the data flow and some key points about the data flow analysis in IMOP. So as many of you might be knowing, iterative data flow analysis is a very important class of compiler analysis. And IMOP provides a set of generic IDFA passes, which are flow sensitive as well as interthread in nature, as in they take care of OpenMP semantics internally. So with the help of these generic passes, one can easily extend these generic passes and implement their custom passes. Like, let's say if you come up with a new IDFA for serial programs, you can extend any of these generic passes, and only with the logic of its serial semantics, you can implement a new pass, a new data flow analysis, which will automatically have the OpenMP semantics in it. So that's one key guarantee which is given by IMOP for all the existing and new data flow analysis. Second is the internal states of these analysis will be self-stable. So I think we had discussed this earlier somewhere. So let's say if I'm unrolling a while loop, and because of that, let's say if I have made some changes, or if I am optimizing the program and I have transformed the program by removing or adding some excesses, the points to information needs to be changed, or let's say the liveness information needs to be changed. These changes will happen automatically because of the self-stabilizing feature of IMOP. So this sounds like magic, but this is some very simple concept. But it will be difficult to go into that concept right now. So I encourage you all to please go through the tutorial and the technical report. Plus, we have a manuscript which we can share if you are interested to go through the self-stabilization feature of IMOP. So now let's look at what are the key components we want when we want to instantiate a generic data flow analysis pass. Let's say I want to implement a new type of points to analysis, or a constant propagation pass, or any other new pass of my own choice. In that case, all we need to specify when working with when extending the generic passes is, first of all, the structure of the flow facts. What is the exact structure of the information that you want to capture with the help of your data flow analysis at each node? Second, what's the value of the top element in lattice? If you haven't encountered these terms, please feel free to ignore these bullet points. Then third is, what is the meet operation? Like, how do we define the meet operation given any two flow facts? Then finally, what is the notion of equality of two flow facts? When are two flow facts equal? And what are the transfer function for various kinds of CFG nodes that may be present in the program? So if you notice, nowhere here had I talked about OpenMP at all. So that's something which is taken care of internally, as I had mentioned earlier. And similarly, self-stabilization is taken care of internally. We don't have to write the data flow analysis driver code, the one where we keep collecting the nodes and updating the flow facts and then keep collecting their successors or predecessors. We don't have to do any of that. We just have to provide definitions for these 5 elements and our analysis would be ready. So we have many instantiations of generic passes already in IMOP, such as points to analysis, teaching definitions, liveness, dominator, log set, copy propagation, heap analysis, and we have a bunch of more analysis. I would really encourage you people to, so for this particular session, we have, sorry, for the section of data flow analysis, we have a detailed introduction in our code manual that we have on IMOP's webpage. So I would want to suggest you guys to go through that particular section and then try implementing an analysis. And I hope you'll be able to appreciate the usage of the generic passes that IMOP provides. So now coming over to the point of stabilization. So what exactly is stabilization? During compilation, we have multiple optimization passes involving analysis as well as transformations. So these transformations will rely on the results generated by these program analysis, rely in terms of correctness, efficiency, precision, and so on. So now in general, mainstream compilers will not automatically update any of the program abstractions, such as the results of program analysis or any of the program representations automatically in response to any of the program transformations. So for example, if I do constant replacement, let's say I had a statement x equals to y plus z. Now I know that y is 2 and z is 3. So I might want to change it to x equals to 5. As soon as I make this change, as soon as I replace x equals to y plus z with x equals to 5, now the liveness information needs to be updated because y and z are not required at this point anymore. So this is something which none of the existing compilers, excluding IMOP, would do automatically. In IMOP, as we have mentioned, this stabilization will be done automatically. And now the onus of doing these stabilizations would be on the compiler writer. They will have to answer these three questions. First is, what all abstractions need stabilization in response to transformation? So for example, if transformation is constant replacement, the abstraction is liveness analysis in some cases. How to stabilize an abstraction? Like given any change in the program, how do I change the liveness information? So I can either invalidate the whole thing, like the way LLVM does, or I can do an automated update instead of an invalidation of the information. So IMOP by default performs automated update for most of the analysis that it uses. And it also supports stabilization, invalidation, when invalidation is the more efficient choice. And third is, where should we write the stabilization code? So this is a very critical point, because the compiler writer who is going to write, or rather the pass writer who's going to write the liveness information, and the one who's going to write the code for, let's say, constant replacement, they might not know who should take care of the changes. Is this a responsibility of the pass writer for liveness analysis, or is this the responsibility for the pass writer for the constant replacement transformation? We do not know. And in fact, I mean, there can be wars because of that. So IMOP tries to prevent such wars by taking care of all these things internally. And the major issue is, as soon as we, so all the compilers are ever evolving. And whenever we add a new analysis or new transformation, we'll have to again go back and see, like, let's say if I add a new analysis, I will have to now go through all the existing transformations in the compiler and make sure that my analysis is not getting impacted incorrectly because of any of these transformations. As in, once the transformation is performed, my analysis data remains consistent. So that's the responsibility of the analysis writer now. Similarly, once I add a new optimization, I will have to go through all the existing analysis, for example, points to or liveness or reaching definition, and then see how shall I change these analysis as a result of the application of my transformations. So these are the things which a compiler writer will not have to worry about in case of IMO. So I hope this notion of self-stabilization is clear. So in IMOP, as I have mentioned, we will not have to write, a compiler writer will not have to write any code to ensure self-stabilization when adding new transformations. And then similarly, when you're adding new data flow passes, you won't have to write any code. For other analysis and abstractions, other analysis and representations, we can automatically trigger the invalidation when we talk about some new abstractions. Or there are some ways in which there are some well-defined methods which we can implement to again trigger the incremental update rather than invalidation. So this is about self-stabilization. If we have any questions on this, we can take them now.
Naman, in terms of for data flow analysis, did you consider the phases as well? I mean, I'm just curious to know.
Yes. Phases are required. See, because data flow analysis is all about the way data flows from one point of program to another, right? So now in case of OpenMP semantics or OpenMP programs, under the semantics of OpenMP, data can flow between two program points which are not connected via the control flow graph or call graph.
Yes,
So,
exactly.
so now what we do is we already model these intertask edges, and these edges are created only among the statements within a phase. So yes, we internally use phase as well as intertask edges automatically. And in fact,
Like,
that's the key difference between OpenMP semantics versus serial semantics when it comes to data flow passes.
true.
One of the key differences. Another one being that we can have multiple copies of stack when we talk about OpenMP.
And in terms of the lattice values that you specified, that the user might need to provide some values. So like
Yes. If you'll,
top
So I will
value.
go back. Yeah, these things. Yes.
So is it like the top value is like is it to uh, like put a restriction on the time execution time of the analysis, or I mean to limit the height of the lattice, or
No,
and
this is about the height of the lattice to make sure that the analysis terminates. So we are talking about the standard IDFA passes. So there we usually will have a top element which will signify unknown values.
Yes,
And
yes.
so this is that top element. So for your
Yeah.
specific analysis, yeah.
So can a user put a value, like suppose for uh, like based on the accuracy someone prefers? So the
Yeah, I think those things can be done. Like to be honest, I haven't tried that experiment yet, but I think that can be done once you specify. I mean, if you want to change the value of the top element depending upon the invocation or the current state of the data flow, you can do that. But then I'm not sure whether there will be termination guarantees or guarantees of the fixed point uh, in that particular formulation.
yes, yes, I see.
So in general, this in case of standard data flow analysis, the top element is usually fixed for any given lattice. I mean, that's the standard formulation, but doesn't mean
Yes,
that that's most useful in all the cases. It works for many cases. There might be some cases where we might want to change it during the analysis.
right, right. So like these are already defined for the standard passes that you have shown, the
Yes,
standard
yes. Yes. So
analysis.
for points to reaching definition, constant propagation, copy, liveness, dominator, log set, we have two or three more. So yeah, for
And
those, these things are
concurrent.
different. Concurrent, no, so concurrency is implicit in all of these.
Okay,
Like,
okay.
yeah, so as I mentioned, intertask edges are taken care of internally. And those are the edges which determine the communication between different tasks or threads. So regardless of what data flow analysis you pick, existing one or a new one that you write, if you're implementing it in IMOP, there is no way you can escape the OpenMP semantics. It will automatically be enforced internally. So that's a good thing. That way you won't have to worry about the cross communication between two program points. It
Right,
not
right.
by control flow graph.
And I mean, the data sharing part was not specified. So maybe it is also handled internally
Data
for.
sharing is, yeah, we do have data sharing attributes for symbols. So I had skipped it while explaining that. But at any given node, the data sharing attributes, whether it is a shared variable or a private variable, that thing can change depending upon the program point where we ask that query. So given a symbol and a program point, we can get its data sharing attribute. So there is a method in the miscellaneous class or also in the symbol class. So using that, we can obtain the data sharing attributes.
Right, right. Nice.
Okay, so moving on to the next other interesting features of IMOP. So, I mean, these are just a subset of many features that I wanted to talk about, but we have finite time. So first is the Lambda-based generic graph collectors. So this just uses the Lambda functionality in Java. And it's a set of functionalities where we automate the graph traversal mechanism for frequently occurring traversal patterns. So for example, if you know what are the, so let's assume an abstract graph, we do not know the node type, we just know a starting node and we know what's the condition, end condition, where the traversal has to be terminated. So we can perform such traversals on such templates with the help of these functionalities. Later, you can use that template for, let's say, traversal on an AST versus traversal on a CFG and so on. It can be any data structure of your choice, any data type of your choice. So maybe it wouldn't do justice to discuss Lambda-based generic graph collectors without examples, but because of time, we won't be able to do that. So I encourage you all to please check it in the code base. And second, one of the very important things here is the interface or integration of IMOP with the Z3 SMT solver, which is by Microsoft. So many compiler analysis can be represented as a system of constraints. So as maybe you would have learned about such system of constraints when talking about data dependencies across statements having array accesses in a loop. So if you recall, we used to have some inequations and all in those analysis. So in a sense, in fact, all the compiler analysis can be represented as a system of constraints. And now the key question is, who will generate these constraints? It's usually difficult for a compiler writer to generate constraints like this. For example, if I have a while loop and I want to do dead code removal, the constraint will be, is the predicate not equals to 0 or equals to 0, depending upon the way we are making the formulation. So given this seed constant, let's say that the predicate is not equals to 0, we'll have to generate the inequations based upon the variables used in the predicate. So this is something that IMOP can do automatically. Given one or more seed constants, it can automatically generate the underlying system of inequations. So this involves many things, including solving the recurrence relations. So for example, in inequations, you can't have something like I equals to I plus 1, because this is pure maths where we have only one value for one variable. So we will instead have another form where we won't have recurrence of that nature. And then after generating such underlying system of inequations from the given seed constraint, IMOP will then invoke Z3 SMT solver by converting these inequations to the proper format, and then obtain the response from Z3 and return it back to the compiler writer. So that way it becomes quite easy now, because now you don't have to worry about creating the system of inequations. You won't have to worry about how to solve those system of inequations. All you need to say is ask a query in terms of C expressions, like expressions at the higher level. Once you have that query or a constraint, once you feed it to appropriate interfaces, IMOP will automatically perform the invocation and give you the response. Obviously, when we call it via the proper interfaces. So this is used for, in practice, we have used it for dead code removal and for adding field sensitivity to various analysis. It can also be used for auto parallelization and many other such features. So this is about Z3. Again, this is a very complex topic which can have a tutorial on its own, but because of lack of time, we cannot show an example right away. So now what we have done so far in this tutorial. So we have used the parser of IMOP to perform pretty printing of a pass and perform simple queries on the AST. Then we have understood how the nested control flow graphs and call graphs work in IMOP and how we perform traversals and queries on them. Then how we work with the scopes, symbols, and types, how we work with memory abstractions, how we create new code snippets and perform simple as well as higher level transformations in IMOP. And how do we utilize the concurrency analysis in IMOP? And we also looked at some of the key features without going into the hands-on session for those features. So we have miles to go. So to summarize, IMOP is a, sorry. Yeah, so IMOP is a source-to-source compiler framework for OpenMP programs. We have used some of its key features. So I am the developer of IMOP, and under the guidance of my thesis advisor, Krishna Nandivada. Total size of IMOP is 154 KLOC, and I have coded 127 KLOC manually. Rest is generated by the parser, which was the first step. Once you generate grammar, you give it to Java CC/JTB. It's a parser generated by a compiler group at UCLA. And once you obtain the parser, then you have to build a framework on that. So that building task was this much. This was released during the last CGO tutorial on 22nd Feb. So we have the official website at imop-iatm. This is the bit.ly link, and the GitHub repository at imop-compiler. So what next? So clearly, we do not, for example, handle all the possible OpenMP constructs. It's a very fast evolving API, a very useful API. And we require contributions from you all to help us add the missing constructs and directives, help us increase the width as well as depth of the framework. So please try it out and contribute towards enhancing the quality and capabilities. And please let us know if you have any suggestions for the framework or this tutorial in general. Thank you. So we can have some questions now. In case if you have any questions, we can take them now.
Yeah, like very excellent presentation and like walkthrough of your code, and I mean it's a very good introduction to some topic. I really appreciate your effort in this.
Thank you.
Thank you all for all the questions as well, for all the audience, especially to you.
Yeah, I mean really would have taken, see, for us, it's like we already know the topics and we are just speaking about them. But for you guys, you were with us for like long 4 hours and like learning a new concept every now and then. Must be very mentally tiring. So thanks a lot for attending. And thanks a lot for trying out the hands-on sessions.
So I have a couple of questions. Can I,
Yeah,
if
please.
it's fine,
Yeah,
is
please,
it,
please ask.
or are we getting late?
No, no,
Maybe.
no. We have time.
Okay. So
We have time. Yeah.
if I get it correctly, the Z3 solver was, is it used to get MHP information for the loops, or what we, I mean, condition vectors? Is it?
We haven't used C3 in that form. Instead, what we have done is we have used C3 to resolve some data dependencies when we are
Okay.
talking about, say, array accesses. So that's one of the major reasons why we had added Z3. But
Okay.
now it's in a generic form, so we can use it for writing an MHP analysis as well.
All right. All right. And another question was, yeah, related to, like, generally, uh, not all the loops are amenable for transformation or parallel parallelism. So maybe
Yes,
like loop skewing is one of the very common uh,
yes, yes.
transformation which will enable parallelism or introduce some kind of parallelism at least. So like, have you tried any such transformation, like automatically?
Auto parallelization as such was never one of the projects that we got time to look at, but
Okay.
it's indeed something very useful. But see, I mean, if you look at other compiler frameworks like Setters or Pluto, they perform auto parallelization quite well. And there are many others, I'm sure, which I'm forgetting the names of right now. So we do not as such focus on auto parallelization because that's something where you start with a serial code and then try to parallelize it to OpenMP. Most of the compiler frameworks perform that already. What we were concerned with that, okay, once you have the OpenMP code, what next? Do we have a compiler framework where you can make sure that OpenMP semantics are not broken anywhere? Sorry,
Okay.
anywhere in the class.
Right, right.
Yeah, auto parallelization is indeed one of the interesting projects, which I hope someone will like pick up and start writing auto parallelizer codes within IMOP.
Yeah. I mean, see, Utpal, the way to look at it is this is just the beginning, right? I mean, a lot of things that can be written. And
True.
since IMOP is working at a higher level syntax, lot of the abstractions that we lose out once we go to the higher level, they're all visible. So um, uh, we can definitely think of doing more things, say syndization or auto parallelization or all these things. And now with OpenMP, with this new task model and all that, definitely this is,
Yes.
I mean, this is something that is very much in, I mean, within the range. You see what I mean?
Yes, yes. I think there's a lot of possibilities with this.
Yeah, yeah. Again, I think it's the key is not that everything is done. The key is a lot of things can be done.
True, true.
So, if any of you want to send us an email, I'll just type our email address for IMOP. I forgot to add it over here. So, if you have any comments, suggestions, queries, anything you want to talk about, please send a mail to imop@csc.iitm.ac.in. Okay. So, Krishna, shall we wrap up then?
Yeah, sure. Unless there are any further questions, um, I think we should thank all the audience. Thank you very much for sticking with us.
Thanks.
Online tutorials are this is the first time we are doing online tutorial. We have
Yeah, I
no
mean,
clue.
yeah, it's really bad that we aren't able to meet you people face to face because I mean, this
Yeah.
feels as I'm talking to the screen.
Yeah,
But,
True.
yeah, I think, yeah.
but I mean,
Good for
seriously, it's a new experience for us. Hopefully, it wasn't too bad for you guys too. And thanks for sticking with us. Hope you guys find the tutorial useful, and if you need anything, please feel free to reach out.
Yeah.
Okay, thank you very much. Have a good PAT CC HPC.
Yeah, and hoping to meet all of you guys somewhere in some conference near.
Yeah, sure.
So, thanks
Thank you.
everyone. Bye.
Okay,
Take care.
thank you.
Bye.
Thank you guys too.
Thank you.